Mirabai Space Center. Okay, these are the institute available after BSc Physics. Career options after BSc Physics in government sectors. Okay, you know what is meant by DRDO and Physical Research Laboratory, Saha Institute of Nuclear Physics, and Indian Space Research Organization, and the Nuclear Science Center. Next, the Baba Atomic Research Center, then Oil and Natural Gas Corporation, Bharat Heavy Electricals Limited, National Thermal Power Corporation. And if you complete your BSc degree, any degree, you can join. You can apply for Indian Forest Service and UPSC Geophysics exam. Then these are the few private sectors or the important private sectors available after completing your physics degree. The analog devices, G Digital, Tesla, Solar Industries Limited, and Tata Consultancy Services. Okay, after your BSc successfully completing your BSc degree, you can join MSc degree in IITs and NITs through JAM exam, that is Joint Admission Test for MSc. So if you are interested to join in central universities, you can you have to write the Central University Common Entrance Test. Then you can join in the central university for your MSc degree. These are the list of the courses. Not only this, there are various courses are available if you are interested to do your MSc degree. The physics, applied physics, biophysics, geophysics, and material science. There are several courses available for your Master of Science degree. So what are the scope after clearing your gate in physics? Okay, if you clear your gate with a high grade, okay, you can join for a foreign universities after your gate exam. And if you are interested to do your research, you can join research. And if you are interested to do higher studies, you can do your higher studies after clearing your gate exam. Then the summer internship, the Indian Academy of Science and various other research institutes offer a paid summer internship for science students to get a hands-on experience in research. These are the abroad summer internship for students pursuing UG course in physics, the NASA, LIGO, and CERN, National Aeronautics and Space Administration, LIGO, the Laser Interferometer Gravitational Wave Observatory. CERN is nothing but European organizations for only nuclear research. After successfully completing your BSc Physics degree, you can join ISRO as a trainee, and you can apply for a Raman Research Institute and NPL. You can apply for BORC and HRI or Inter-University Center for Astronomy and Astrophysics. Then after completing your PG degree, okay, you can apply for Indian Institute of Science, then Indian Institute of Technology, then Indian Institute of Science Education and Research. Then the various institutions are available in India. Then Igcar, you know that the Indira Gandhi Center for Atomic Research in Kalpakkam, the National Institute of Technology, then Physical Research Laboratory, the Institute of Plasma Research in Gujarat. And the Raman Institute, Raman Research Institute, then the Indian Association for Cultivation of Science, the Tata Institute of Fundamental Research in Mumbai, SN Bose Center Basic Natural Science in Kolkata, then the Indian Institute of Space Science Technology in Kerala, Indian Institute of Astrophysics in Bangalore. Then CSIR Academy, there are several national laboratories are available, few of them in Delhi, Hyderabad, Chennai, and Trivandrum and Calcutta. Then you can do your research in central universities or state universities. Then these are the common entrance tests after completing your postgraduate in physics, CSIR, the UCNet, the JAM exam, joint admission test already said. Then just joint entrance screening test. Then GATE exam, graduate aptitude test in engineering. The exam conducted by the respective universities. Okay, the faculty questions are not the common career path for physics. Several industries are available after completing your BSc Physics or MSc degree. Choose your right path, students. Thank you.
பாபா சண்டை சண்டை இல்லைன்னு சொல்லுங்க சந்தோஷமா ப்ளீஸ் சண்டை இல்லைன்னு
Saravanan sir, mute yourself, sir.
ட்ரை சார் கேட்கலையா பேசுறது?
கேக்குது
இல்ல இப்போ முன்னாடி பேசினா கேட்டுதா?
கேட்டது sir. Clear ஆ இருக்கு.
Sir, we hear you, sir. No problem, sir. Please go ahead. Yes, sir. Please go ahead.
Okay. Thank you.
Sir, once again, Nadra sir, if you, Nadra sir.
Yes, sir.
Please assign the co-host to Parameshwaran sir, Karthik sir, and Anita madam, please.
Yes, sir.
Okay. Thank you, sir. Thank you. Sir, Ranjit sir, please go ahead.
சொல்லுங்க.
Nadra sir, are you able to hear me? Nadra sir?
Yes, sir. I am here.
Yes, sir. Fine. Announcement for the participants.
Saravanan sir.
Yes, ma'am.
Sorry to disturb you, sir. Good afternoon, Dr. Parameshwaran sir.
Parameshwaran sir.
Dr. Karthik sir.
Yeah, good afternoon. I'm in. Yeah, you're able to hear me?
Yeah, Dr. Karthik, welcome. Good afternoon.
Thank you. Yeah.
Dr. Anita.
Hello.
Good afternoon, Dr. Anita. Welcome.
Yeah. Thank you, madam, and good afternoon to you too.
Dr. Parameshwaran sir. Good afternoon, sir.
Good afternoon, ma'am.
Sir, sorry, sir. I had faculty recruitment interview.
जैसे नहीं होगा लेके कितना बहुत बात करेंगे
Hello. Good afternoon, ma'am.
Sir, we are hearing, sir.
Hello.
Sir, we are able to hear.
Good afternoon, sir.
Good afternoon, sir.
Sir.
And dear participants, you mute your mic and video also. Dear participants, mute your mic, audio, video both.
Hello? Yeah. Yes, yes. You're able to. Okay, right. Yeah. Yes, sir. I've seen that. Thank you.
Dear participants, the YouTube streaming is also turned on. Now it's streaming. I request the participants to turn off their video. HOD ma'am, shall we start, ma'am? HOD ma'am, Sudha ma'am, shall we start?
2 minutes, sir.
Yes, ma'am. Okay, fine, ma'am.
You are seeing slide now, sir.
Yes, sir. No problem, sir. No problem, sir. I request all the participants to mute your audio. Ma'am, shall we, ma'am? HOD ma'am.
Sir.
Shall we start, ma'am?
Yes, sir.
Okay, fine. Yeah, very good afternoon to one and all present here. First and foremost, I welcome to all for virtual workshop on Indian nuclear program in association with Indian Institute of Metals, Kalpakkam chapter, Igcar. I am Dr. M. Saravanan, Assistant Professor, Department of Physics, SRM, Institute of Science and Technology, RAMAPURAM campus, and also Organizing Secretary of this workshop. Education is all about creating an environment of academic freedom where bright minds meet, discover and learn. One would experience top of the world living and learning experience at SRM. SRM Institute of Science and Technology, formerly known as SRM University, is one of the top ranking university in India with over 20,000 students and 1,500 faculty, offering a wide range of undergraduate, postgraduate and doctoral programs in engineering, management, medicine and health sciences. The Ministry of Human Resource Development, Department of Higher Education, Government of India has placed SRM Institute of Science and Technology in highest category A. This is indeed a proud moment for SRM Institute of Science and Technology. And also, SRM is accredited by NAC A++ grade in the year 2018. Now, the Indira Gandhi Center for Atomic Research, IGCAR, was established in the year 1971 under the Department of Atomic Energy, Government of India. IGCAR located at Kalpakkam in the second largest R&D establishment of the Department of Atomic Energy. The mandate of IGCAR is to conduct broad-based scientific research and advanced engineering development towards sodium-cooled fast-breeder reactor technology. Over the years, the center has established comprehensive R&D facilities covering the entire spectrum of the FBR program related to sodium technology, reactor engineering, reactor physics, metallurgy and materials, chemistry of fuels and its materials, fuel processing, reactor safety control and instrumentation, high performance computing, etc. Apart from pursuing mission-oriented technological development, a strong emphasis is placed on the basic research as well. The center has credentials as a leader of research in various frontier and topical subjects like oxide superconductors, nanostructures, nanoclusters, superconducting quantum user interference device fabrication programs, exopolymers, and experimental simulation of condensed matter using the colloids, etc. According to the IIM, the Kalpakkam chapter of the Indian Institute of Metals was founded in February 1982 with Dr. Plazit Rodriguez as its founder chairman. Under the guidance and able leadership of many eminent chairpersons, the chapter continues to be very active over the last many years and has grown in stature and strength. Today, it has a total strength of over 200 members that include around 150 life members. The major activities and programs of the chapter include the Professor Brahm Prakash Memorial National Level Materials Quiz, Memorial Lectures, Metallurgy Colloquia, workshops, teams, meetings, and short courses on metallurgy and joint technical events with other professional bodies. Now, I request Dr. L. Sudha, Professor and Head, Department of Physics, and also convener of this workshop, to give the welcome address and overview of the virtual workshop on Indian Nuclear Program in association with IIM Kalpakkam chapter, IGCAR. Ma'am.
Good afternoon to all who have joined this virtual workshop on Indian Nuclear Program organized by Department of Physics in association with the Indian Institute of Metals, Kalpakkam chapter, and Indira Gandhi Center for Atomic Research, Kalpakkam. First and foremost, today I welcome Dr. P. Parameshwaran, Head Physical Metallurgy Division, IGCAR, Kalpakkam. Thank you, sir, for accepting our invitation to be with us today. And he is going to enlighten us on selection of nuclear materials. On behalf of Department of Physics and on behalf of SRM IST, I welcome you, sir, Dr. Parameshwaran, sir. And Dr. Parameshwaran sir has joined Baba Atomic Research Center, Mumbai as a trainee in 1985. On placement at the Indira Gandhi Center for Atomic Research, Kalpakkam in 86, he started his career as a scientific officer in physical metallurgy section. And we are associating with Dr. Parameshwaran sir for the past 10 years. And his present interest centers on microscopic characterization of nuclear materials, spark plasma centering of nuclear ceramic materials, structure property correlations, plasma nitriding of engineering compounds, and engineering failure analysis. We have also done a workshop of failure of materials in association with Society for Failure Analysis. And I extend a cordial welcome to Dr. V. Karthik sir, who is going to enlighten us on mechanical behavior of nuclear materials. And he is a currently senior scientist at Indira Gandhi Center for Atomic Research, Kalpakkam. His research interests include mechanical behavior of materials using conventional and small-sized specimens, nuclear materials of fast reactor, and analysis of their in-reactor performance. And next, I extend a cordial welcome to Dr. Anita Tapu, who has joined Indira Gandhi Center for Atomic Research Department of Atomic Energy in 2001. Since then, she has been involved in carrying out research work in stress corrosion cracking of austenitic stainless steels, ferrite steels, and their weld materials, and non-destructive evaluation of corrosion using eddy current testing, acoustic emission, and electrochemical noise techniques, and corrosion audit of structural components. She is going to deliver lecture on environmental effects on performance of nuclear materials. This is a most very important topic because many people are having fear for these nuclear materials. So the environmental effects on performance of nuclear materials is a most important topic. Hope this will be well received by the participants. And also I extend a cordial welcome to all the participants, school students and teachers from schools and other faculty members from other institutes and universities. And coming to this Indian Nuclear Program workshop, India seems at nuclear skill and nuclear materials principally as a resource for meeting a fraction of its necessities for electricity. It considers nuclear power as secure, consistent, affordable, and environmental friendly, and is occupied in emerging nuclear technologies for exploitation. In tune with the security requirements as perceived by India, the nuclear security architecture in the country has been strengthened, and India has also participated in strengthening security architecture at the global level. Hope from this workshop, the participants will be able to enrich their knowledge in the selection of nuclear materials, some knowledge about selection of nuclear materials, its mechanical behavior, and the environmental effects on its performance. Thank you. Have a wonderful learning.
Thank you, ma'am. Thank you so much for your talk on Igcar and welcome address. Now I request Dr. A. Nadraj, Assistant Professor, Department of Physics, SRM Ministry, RAMAPURAM campus, and also coordinator of this workshop to play our department video. Sir.
So in our department, we have conducted many events in the previous years. So this is the mini project contest we have conducted in the year of 2019. This is the mini project contest in the year of 18. The various school students actively participated in the This is the science exhibition in the year of 2017. This is our department laboratory. We have a 2 lab. So this is the 8th National Conference conducted in the year of 2020, sponsored by CSIR and DRDO. This is the 7th National Conference, which is sponsored by CSIR New Delhi in the year of 2019. 6th National Conference, sponsored by CSIR New Delhi in the year of 2019. 5th National Conference, sponsored by DST Serb and CSIR New Delhi in the year of 2017. This is the workshop on material characterization conducted in the year of 2019. 2 days workshop on structural characterization in the year of 2019. This is the failure analysis of materials workshop. The special lecture on nanomaterial by Japanese scientist in the year of 2018. MNRU workshop, Government of India 2017. Thank you.
Thank you, sir. Now I'm very happy to introduce Dr. P. Parmeshwaran, sir, Head Physical Metallurgy Division, Igcar Kalpakkam. Dr. P. Parmeshwaran obtained a bachelor's degree in metallurgy from PSG College of Technology, Coimbatore in South India. Followed by, he took his master's in engineering from Indian Institute of Science, Bangalore. He joined Baba Atomic Research Center, Mumbai as a trainee in 1985. On placement at Indira Gandhi Center for Atomic Research, Kalpakkam in 1986, he started his career as a scientific officer in a physical metallurgy section. Since then, he has been involved in physical metallurgy study of nuclear materials. Currently, he is head physical metallurgy division. Starting his career with an aim of purifying zircology of hydrogen levels using a solid state technique, namely electromigration, he continued exploring the possibility of improving the oxygen stoichiometry in the essential high temperature superconducting material of the decade. In parallel, he developed expertise in electron microscopy of nuclear materials that he took up a serious study of analytical electron microscopy of ferrite steels, which culminated in his doctoral dissertation. He has been selected for carrying out research at Technical University Graz, Austria by the Austrian Academy in 2002 and later at the Cambridge University by Royal Society, London in 2004. His work at these institutions aimed at using advanced electron microscopic techniques like energy filter transmission electron microscopy, electron tomography, electron holography for characterizing nanoscale phases in ferrite steels. His present interest centers on microscopic characterization of nuclear materials, spark plasma sintering of nuclear ceramic materials, structure property correlations, plasma nitriding of engineering components, and engineering failure analysis. Currently, he is collaborating with his colleagues in understanding creep, fatigue, and impact properties of nuclear materials. His interest in the nanoscale materials and the preparation makes him take part in the characterization of these materials as well as. He has published more than 80 papers in international journals and presented several talks in conference. He has won prizes for his oral post and metallurgy presentations in various conferences. He is awarded National Failure Analysis by SFA in the year 2016. He received the DAE Group Achievement Award for development of high nitrogen stainless steels in the year 2016, development of IFAC stainless steel in the year 2019. In recognition of all his contributions, he has been awarded a certificate of honors by Indian Institute of Metals during his annual meeting at Varanasi in November 2013. He is elected fellow of IIM and Council of Member. He is a honorable secretary of SFA at headquarters and vice chairman of Chennai chapter SFA. In an effort to disseminate the knowledge he has learned, he has been regularly giving talks on electron microscopy at various forums. He has joined hands with the Federation of Science Clubs of Tamil Nadu, a non-governmental organization, in its efforts to spread science among the youth. Further, he joins the local Kalpakkam chapter after Indian Institute of Metals is conducting Brahm Prakash Metals and Materials Quiz every year as a quiz master in one of the initial rounds, thus adding to the efforts in spreading the importance of materials to mankind. He regularly joins science clubs in conducting from Hobi Baba Day with a lecture and quiz. He is invited for a DSC-sponsored programs for inspiring youth conducted by the universities and research institutes for conducting science quiz. Now, I handed over the session to Dr. Parmeshwaran, sir. Sir, please. Permission, sir. Now you can share the screen and unmute your audio, sir. Sir, kindly unmute your mic, sir, so that we are able to hear.
Is it audible?
Hi, sir.
Yes, sir.
Yeah.
Audible, sir.
Shall I start? Good afternoon to all of you.
Sir, good afternoon, sir. Go ahead.
Yeah. Shall I start?
Yes, start, sir.
At the outset, I would like to thank SRM Institute of Science and Technology, in particular, the Department of Physics, the faculties who have gathered to see that this afternoon will be a useful day, sharing some of the things we have learned for a period of 30 years or so in the subject of nuclear materials. For the participants, you have my email ID, param@igcar.gov.in. And if you have any doubts, you can write to me later on in case time is not available at the end of the presentation. I have about 90 slides. I will try to finish it, and I hope I will be able to rush through. Initial 30 slides will be about the nuclear program of India, and then about the materials and its selection. Consider a situation where an airport does not have power. You would find the luggages getting locked up, and such a situation will be very difficult to handle. Though in a country like India, there are many ways a transport can easily move from one place to another, any fragile material, as the next slide shows. If you look at the situation of India right from our independence, we started with electricity production with about 4,172 megawatt electrical, is about 4 gigawatt. Exactly after 50 years in 1997, we are about 84 gigawatt. That we are progressing on our electricity production. However, if you look at the electricity consumption, it's only 300 units, which is about 1/8 of what a world country, advanced country like US consume. If you look at the progress in our electricity production, it is going on, and currently we are producing around 700 to 800 gigawatt, and the rate at which the change comes with around 5 to 8%. And if you look at the electricity consumption by our people, there are about 300 million people who do not have access to electricity. In particular, they are living in villages. If you look at 6 lakhs of villages in and around India, about 1 lakh villages do not have electricity. We aim to generate around 600 to 1200 gigawatts additional power at least by the end of 2050. If you compare ourselves with China, while we have 24% of people do not have electricity, China has only 0.2%. We look at Pakistan, neighboring country, 32%, Bangladesh 40%, Burma is poor, very poor, 69%, North Korea 73%. So we look at ourselves, we are better off, but still we have to improve. So way back in 1944, Homi Jahangir Baba, a great visionary of this country, thought that no power is costlier than no power. And therefore, he proposed a 3-stage program for India. Accordingly, the first stage uses the naturally available uranium in the country, and the second stage is to breed the available material, uranium-238 or thorium-232, into a usable, fissionable material of uranium, that's U-233 or plutonium-239, subsequently run and get electricity. This 3-stage program can help India to sustain electricity for the next 500 years. And he had a very good rapport with Pandit Jawaharlal Nehru, the then Prime Minister of India, and therefore he decided to start Department of Atomic Energy, and Atomic Energy Commission was established, Department of Atomic Energy, with a regulatory board which is very independent, Atomic Energy Regulatory Board AERB. Under the Atomic Energy Department, we have several units, like on the left, Bhavani is basically the 2nd stage reactor, prototype fast breeder reactor is in Kalpakkam, is almost ready for commissioning, and all the other reactors in India are taken care by Nuclear Power Corporation, NPCIL of India Limited. They provide the power, and the source uranium is supplied by mining, Uranium Corporation of India Limited and Indian Rare Earths IREL Limited, which is spread all over India. And people from Tamil Nadu know Manavalakurchi, very near to the Nagarkovil, is a place where a lot of work is going on, IREL. Chavara in Kerala, in Alway, IRE is there. And all these material, when they are properly mined and converted into useful metals, they are converted into suitable pellets and the structurals in which they are placed is at Nuclear Fuel Complex in Hyderabad. And all these things are monitored by the Atomic Energy Regulatory Board. Without their permission, nothing is done. We look at the electricity production from different sources like coal, like water, hydroelectric power plants, wind, biomass, solar, gas, and nuclear and diesel. The nuclear production from the various reactors is around 1.8%. That is 2% of our total electricity. As per 2017, it is around 315 gigawatts. India is worldwide, it is the 3rd largest producer Consumer wise, it is fourth largest. Consumer, we have 17% of our electricity consumed in agriculture, is highest among the world. Per capita consumption still low compared to various countries. If you look at the world statistics, about 11% of world total electricity is done by nuclear power plants. If you look at the United States, it has more than 100 reactors. Although
excuse me, sir, permission, sir.
Yeah,
Sir, screen is somewhat blurred.
blurred. All right. Is all right?
Sir, a little bit, sir. Little bit blurred.
You want me to stop and increase the power brightness, huh? Hello?
Not brightness, sir. I think more contrast is there.
More?
Contrast.
More contrast. Settings.
Saronan, sir, can you have a short PPT? Saronan, sir.
Is it all right?
Sir, still it is blurred, sir.
Somebody can help me?
Saronan, sir. Saronan, sir. Saronan, sir.
Natara, sir. I'm able to hear you.
Sir, for you, the screen PPT is clear?
No, sir. Somewhat blurred, sir. The same, okay, I mean, okay, problem. Okay, here we have. Permission, sir. Able to hear me, sir?
Yeah. I am able to hear you. You tell.
Sir, please, okay, a bit stop share and again, okay, you can share the PPT, sir, once again.
Stop share.
Then, okay, again, okay, you share the screen and you just click the PPT, sir. It means, okay, again, okay, I'm asking you to share the PPT.
Yeah.
Yes, sir, yes, sir. Now it's sharing.
Yeah. Shall I start?
No, sir. Again, okay, the PPT, okay, the content of the PPT is somewhat blurred, sir.
This one? The next one?
No, sir. No, sir. Actually, the PPT is visible, but the content in the PPT, the sentence, the whatever, okay, the sentence in the PPT, somewhat blurred. Not okay. I mean, able to. I mean, visible.
I'm able to see. How best you can do? You tell me. Can anyone help?
Yes, sir. Yes, sir. Sir, have you sent a PPT to my mail ID, sir? Okay, I'll open the PPT so that I can share.
I will reduce the brightness and only brightness is changeable.
No, sir, the content in the PPT I think is not visible. That's why that's the problem, sir.
Focus assist?
No, sir. Sir, okay, sir, no problem, sir. Okay, you please do send the PPT to my mail ID, sir. I already asked it.
I cannot send because it is a heavy file.
Oh, that's the problem.
Parameshwaran sir, can you send to Dr. Karthik or Dr. Anita?
No, it is 25 MB. It will not go through.
You can share it by using Google Drive, sir.
Google Drive is already full for me. Already more than.
Actually, the PPT is visible, sir, but the content is not visible, sir.
So suggest a way.
Sir, this is the only way, sir. If you share the PPT to Karthik sir or Anita ma'am, okay, no problem, sir. Okay, we request the Karthik sir to open the PPT so that you can do a presentation, sir. That's much better. Because from our end, yes, sir. You please do send the mail to Karthik sir.
I'll stop share first of all.
Yes, sir.
Saravanan?
Sir, சொல்லுங்க sir.
Shall we?
Sir, Dr. Parmeshan sir. Sir, if you don't mind, you please do send the mail to Karthik sir. Meanwhile, can I ask Anita ma'am to give her?
Yeah.
Okay, fine. Anita ma'am.
Yes, sir.
Hi, thank you so much, ma'am. Ma'am, I'll give the introduction about Dr. Anita Topu. Dr. Anita Topu joined Indira Gandhi Center for Atomic Research, Department of Atomic Energy in 2001. Since then, she has been involved in carrying out research work in stress corrosion cracking of austenitic stainless steel steels, ferristic steels, and their world metals, and a non-destructive evaluation of corrosion using eddy current testing, acoustic emission and electrochemical noise techniques, as well as corrosion audit of the structural components. Dr. Anita Topu completed her PA or MSc from Pune University in 1998. Then she completed her PhD in 2015 from University of Madras. She has made a number of significant and unique research contributions. She has many papers in international journals and book chapters to her credit. Recently, she received NIGIS Corrosion Awareness Award 2018, the distinction in corrosion science and technology in research and education. Now I hand over the session to the Dr. Anita Topu. Ma'am, please, share your screen.
1 second, sir.
Okay, ma'am. Please share your screen and start your presentation, ma'am.
Share. Are you able to see, sir?
Yeah, ma'am.
So, shall I start?
Yes,
start,
ma'am. Yes, ma'am. Able to see your screen very clearly, ma'am. Thank you so much, ma'am. Please.
Okay, okay. So, yeah, first of all, I would like to thank SRM for giving this chance, as well as I would like to thank my IIM Kalpakkam chapter. They approached me and they told me that I have to give a talk on this topic. Actually, Dr. Sudha madam told that it is the environmental effects because of nuclear materials. I am going to give something slightly different. That means the environmental effects, like our atmospheric effects on the materials which are used in nuclear reactors. So that is what is my topic. That is environmental effects on performance of nuclear materials. So actually this slide shows that there are various factors which are involved when we are selecting a material for nuclear reactor application. So first of the factor is that this material should withstand very high stresses. Generally in reactor there will be different types of stresses like residual stresses or service stresses. So these materials, whatever we are selecting, needs to withstand these kind of stresses. And then the environment of a nuclear reactor is generally high temperature deoxygenated water, or in case of fast breeder reactor, it is liquid metal. So material needs to withstand those kind of environments apart from the coastal and humid environments where our reactors are constructed and are in working condition. And then the temperature in which these materials are exposed to. Generally, the temperature of reactor ranges from 300 degrees C to 600 degrees C in normal operating conditions over a lifetime. So presently, the lifetime of our nuclear reactors which are there in India is 40 years. However, it is planned to extend the lifetime from 40 years to 60 years. So our materials should withstand all these stresses, environment and temperature for a designed life of 60 years. Then previous experiences under similar conditions also is considered, followed by availability is important, affordability, then ease of fabrication. Like some material we have selected, however they are not able to weld properly, or there are many defects in that material that will result in failure of that material, and which is unwarranted. So we need to have these materials which are having very easy weldability and fabricability properties. So today my topic is susceptibility to chemical attack and corrosion, which I will be explaining in next few slides. And once the material is selected, then based on the codes, these materials are designed, and then that also is considered. Toxicity and health impact is also very important when we are selecting these kind of materials. Right. So just for information, I would like to tell that in India, we have 3 different kinds of reactors. First one is the light water reactors. That means here water is used as a coolant. So this is a schematic of boiling water reactor. Sir, can the arrow is seen here? You can see this is a reactor building where fuel is placed in a cladding material which is called as zircaloy. It can be zircaloy 2 or zircaloy 4. It depends on the chemical composition of this zircaloy. So what happens during the fission reaction, heat is produced. And in case of boiling water reactor, this heat will boil the water, and the water evaporates, and then it gets into converts into steam, and then it goes to the turbine and it generates electricity. Then balance of the steam comes back to a condenser, which is again a type of heat exchanger, where steam again gets converted to water, and then this way the chain continues. Here the steam is getting converted and the seawater is used as a coolant in this case. So as I've already told, for cladding material of fuel here is zircaloy. Then pressure vessels, all different kinds of pressure vessels are there, which are made up of low alloy steel with stainless steel cladding. The condenser material which is shown here is Admiralty brass. These are the different kinds of materials. In future, I will be telling what are the corrosion problems associated with these kind of materials. Okay, so now the kind of corrosion problems which have been identified in boiling water reactors is general corrosion of carbon steel. Generally, the corrosion rate ranges from 1 to 2 micrometers per year. Then zircaloy undergoes stress corrosion cracking, which I will explain what is stress corrosion cracking. And then hydriding of zircaloy is also one of the common problems in boiling water reactor. And then it has some 304 stainless steel cladding, which also undergoes intergranular stress corrosion cracking. So these are the corrosion problems in boiling water reactor. Now this is a schematic of pressurized heavy water reactor. It is also a water reactor. So this shows that here again fuel is cladded in a zircaloy material, and feeders and headers are made up of carbon steel. Hello?
Yeah, proceed, ma'am. Proceed.
Okay. Right. So now what, again, as I have already told, during fission reaction, what happens is the energy is produced. With that energy, it boils the water. Here, heavy water is used as a coolant, and then it goes into a steam generator, which was initially made up of Monal 400. However, due to many types of corrosion problems, it was replaced with Inconel 800. So here, steam generator, this heavy water is there in tube side, and shell side light water is there. So this heat is exchanged, and then steam is produced, which runs the turbine, and again it is the same procedure like boiling water reactor. So the kind of corrosion problems here are general corrosion, flow assisted corrosion, then stress corrosion cracking of zircaloy, and hydriding. So past two reactors I told about, the coolant used as a water. Now this is a fast breeder reactor, which Dr. Parmeshwaran was explaining, which is in the commissioning stage in Kalpakkam. So here, the coolant which is used is liquid metal, which is sodium. So here, when a fission reaction takes place, heat is produced, and then liquid metal sodium goes into this is a steam generator schematic here. So here in shell side sodium is there, and tube side water is there. So this water gets heated, steam is produced, runs the turbine, comes back, condenser is there, and then this circuit completes. So in India, we have light water reactors, and we have liquid metal cooled reactors. Here the cladding material, which is the material in which fuel is placed, is alloy D9, which is a type of austenitic stainless steel. And then structural material, like here we'll have this main vessel is there, inner vessel is there. Those components are made up of 316 LN stainless steel. And steam generator material is modified 9 chrome 1 moly steel, which is a ferritic steel. Right. So now topic of Shall I continue? Shall I continue?
Yeah, continue, ma'am.
Yes, ma'am.
Okay,
Yes, ma'am.
fine.
Yes, ma'am. Please continue, ma'am.
Okay. Right. Because I'm hearing some background noise. That's why I thought whether somebody is asking me some doubt or something.
No, ma'am. Parmeshwaran sir is speaking to Karthik sir, ma'am. So just now I muted him.
Sir, mute all the participants.
Right, sir.
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay. Thank you. Right. So now, now the topic of interest is corrosion. Now, corrosion in Latin, it is known as gnaw away. What happens during corrosion is there is a physico-chemical interaction between a metal and its environment. In our cases, generally it is a nuclear reactor environment. In many cases, it is the environment in which the reactors are placed. So there are two types of environment which I will be explaining. So because of this kind of physico-chemical interaction, there is a change in the property of a material and material can degrade. So that is the term why it is called as a corrosion. Now, why corrosion should take place? Actually, corrosion is thermodynamically favorable. Why? Because when we have fabricated a component, this component is having a chemical composition with so many metals and so many alloying elements. So these metals were extracted from the ore. So ore is basically having a very free energy state, lowest free energy state. We are extracting the metal and then we are making into a component. So we are increasing the energy state of that material. And all the materials, or anybody for that matter, needs to come back to their ground level. Hence, these materials also tries to come back to their original space. That is, they want to be in the form of oxides, and hence all the materials corrode. So corrosion cannot be avoided. Only thing is, it can be delayed. That is the important point. Right. So what happens because of corrosion is there is a loss in appearance, and then also chances are that there will be a loss in load bearing capacity. Here I have listed some of the disadvantages of corrosion, like because of this kind of corrosion, destruction of components and structures can take place, which in turn will result in loss of production time, and also resulting in unplanned shutdowns. And in many cases, if catastrophic failure is there, there will be a loss of life along with monetary loss. So corrosion need to be addressed very stringently in these kind of reactor applications. Okay, apart from that, there are some advantages also of corrosion. Like if we know the material in what range it is protective, we can apply externally some potential and we can cathodically or anodically protect the material. Apart from that, we can use sacrificial anodes. And then because of these kind of corrosion problems, we try to develop newer materials, newer processes, or some kind of surface modification techniques which can prevent these corrosion problems. This is a very simple thing, but okay, how corrosion takes place? It is a electrochemical nature. That means this is a metal which is undergoing corrosion, which takes place in anode. So here M is in its +1 form, and it produces electron, it goes to M2+. So during oxidation, there is production of electrons, and simultaneously there is like here now metal electron is absorbed, metal ion, it absorbs electron, goes to its metallic form. And in many cases, these are the conditions of environment where if it is acidic, then it forms hydrogen, and in presence of oxygen, it forms water and hydroxide groups. Okay. So now what are the factors which will influence corrosion? I have categorized into two places. One is environmental factor. That is the medium in which the material is exposed to, the concentration of that electrolyte, pH, temperature, velocity, microbial features. This is very important when we are selecting a material for nuclear reactor application. In my initial slides, I showed that there is one component which is condenser, where steam gets converted into water by exchanging the heat with seawater. So what happens in condenser, seawater is taken, and along with seawater, many times these microbes also come and they get attached to our heat exchangers which is present in condenser. So in that case also, corrosion of those materials takes place because of this kind of microbial adhesion. Then metallurgically, how corrosion is influenced? First is composition, then microstructure, inclusions, segregation, defects, residual stresses, and then grain size. Okay, this is another important diagram, which is a Pourbaix diagram, which is potential versus pH. So this is for iron. It shows that iron, if the pH is very high, what kind of corrosion products will be forming. So this diagram tells the spontaneous direction in which the corrosion will take place. Secondly, the corrosion products which will form in that particular condition of potential and pH. And also very important is that it will tell the environmental changes that can be prevented or reduce the corrosion degradation. Hence, in many cases, this Pourbaix diagrams are used. Okay, so now I have told about the types of reactor, the kind of material we are using, and why corrosion is taking place, the factors which is influencing. Now, something about the corrosion problems which are occurring in our reactors. So this is flow-assisted corrosion, which generally takes place in boiling water reactor. So in boiling water reactor, carbon steel pressure piping system is used, and this carbon steel generally will have a magnetite layer on its surface. But because of very high velocity of high temperature deoxygenated water, in case of boiling water reactors, here the schematic is shown here. We have many places where wells are there, and then you can see that so many bends are there. And when the water flows with very high velocity, it impinges on these localized areas and it dissolves the oxide, which is a magnetite film. Like here it is shown. So this is a metal here, and fluid is flowing with very high velocity. You have a magnetite protective film, and when water flows with very high velocity, it impinges and it takes away or dissolves the magnetite layer which is present on its surface, resulting in this kind of pipe thinning. And because of pipe thinning, many times there will be pipe leakages or burst, or it can lead to a catastrophic failure. So this kind of corrosion problem can be avoided by a term called hot conditioning, which is often carried out in boiling water reactors. So what they do during hot conditioning, which is during shutdown conditions, they allow this oxygenated water with some hydrazine, which is alkaline in nature, to at some particular temperature to flow through all these pipelines for some 5 to 6 hours of duration. And then in that case, what happens, a very good protective film is formed on the surface of carbon steel pipelines, and then flow assisted corrosion is avoided. And in many places now they are replacing this material, carbon steel, with stainless steel, because stainless steel has a very good passive film, which is chromium oxide. In that case, this kind of flow assisted corrosion problems are not there. So this is a corrosion problem in boiling water reactors. Now I will come to fast breeder reactors. Our prototype fast breeder reactor, which is in Bhavani, is in commissioning stage. But initially what we found is that these components were fabricated and they were brought to the offshore areas and they were stored there. So during storage also, there are many kinds of corrosion problems which takes place on these materials. So those kind of problems now I will be discussing here. First of all, there is a pitting corrosion which takes place on these materials. Now, the material of our interest here is austenitic stainless steel, which has a very stable protective passive film. Because it is stainless, it has a chromium percentage more than 12.8%. So it forms a chromium oxide. In some conditions, what happens if there is some inclusion content or there is some burr, then this metal reacts with the aqueous or coastal humid atmosphere and it goes into its ionic form. And since it has some water droplets and dissolved oxygen is there, it forms MOH. And then the pit has started growing. This is the way it phenomena takes place. Pit starts growing, and the opening of the pit, what happens? There is no further oxygen present. It is mostly all these problems are in the micron level. So here, when no oxygen is there, chlorine ingress takes place, and then it forms MCl, and with aqueous environment, it forms MOH plus HCl. HCl is acidic in nature, so this results in autocatalytic activity of pitting, which is very dangerous. And so to take care of this pitting corrosion, initially what is done is pickling and passivation of all the components is done. And in pickling condition, what happens? The component after fabrication, they will the standard is there where they will completely they will use nitric acid as well as HF to completely remove the passive film which is formed on its surface, and then which is followed by passivation, in which again nitric acid is added, which forms a very good thick adherent film. And generally this film is 4 to 5 nanometers size, but it is very stable. So this is a type of pitting corrosion. Here, as you can see, this is a turbine blade where numerous pits are there. So this can be avoided if the component is pickled and passivated very nicely. Now, crevice corrosion is also a type of pitting corrosion. Here, only the geometrical sizes matter. This is a stainless steel gasket. On top of that, many a times some rubber sheet or something is placed. So what happens between the rubber sheet and the stainless steel gasket? There is some localized areas where the medium can go and it can attack the steel and result in these kind of defects. So many dots are there, which is because of the places where the gasket was seeing those kind aqueous environment. And these kind of corrosion problems lead to pinholes and in many cases cracking or leakage of flange joints. Okay, now pitting corrosion studies can be done in our laboratory. So what we do is, here I will show you the schematic. Metal, for example, stainless steel is exposed to a medium. As I have told, chlorides are very dangerous. So metal is exposed to a medium which is sodium chloride, and then since it is a metal, it has its own potential. Then we polarize the material. When we polarize, since it is a stainless steel material, initially some dissolution takes place. So this is the active peak. And stainless steel means, I have already told, it forms a passive film. So the material starts passivating, and this is a passive film. And then beyond some particular potential, this material undergoes pitting. So from this, we calculate the pitting potential. Then we also calculate in different kinds of electrolyte temperatures. So pitting temperature, and then pitting factor is determined is depth of the deepest pit to the average penetration, which is calculated based on weight loss method. Apart from that, pitting resistance equivalent number is also very important, which depends on the chemical composition of a material. If stainless steel has very high nitrogen content, it forms a very good stable protective film, resulting in very high Pren number, and hence that material is more stable. Okay, pitting corrosion can be avoided by cathodic protection, which I explained earlier also. Like if we know that this is a region where the material is undergoing pitting, we will apply a potential somewhere very low here, as it is written here, cathodic protection, and then the material doesn't undergo pitting attack. Also, we can use some inhibitors, or we can go for better materials to avoid these kind of degradation. Now, this is intergranular corrosion. This is another form of localized corrosion attack, and this also takes place in stainless steel material. So this see here, this is a grain. When if we see microstructure, if we see under optical or under scanning electron microscopy, we will be able to see the grains. So in the case of stainless steel, what happens is that when during welding or during some kind of heat treatments, the material sees a very high temperature. Generally, during welding, they go up to some 800, 900 degrees C. So, between the range of 550 degrees C to 850 degrees C, there is a tendency of this material to form chromium carbides. And because of this chromium carbides, which forms along the grain boundaries, these materials get sensitized. And once these materials are sensitized and they are exposed to environment, this corrosion takes place around the grains. And hence, grains are seen like this. And then material properties deteriorates. So this is also showing that when we increase the heat input, generally this is during welding, if we increase the heat input, sensitization increases, as well as the interpass temperature. That means between when we are doing, one pass is there, it is a bead type deposit, so one pass will be there, and then we will wait for some time, then second pass will be done. And in those conditions, if the interpass between the two passes, if temperatures are very high, then also chances of sensitization is there. This just simply, I just wanted to show that sensitization can be influenced by different kinds of treatments. Like here it is, okay, this is first of all very important TTS diagram, which is temperature time diagram, which is given for to identify the zone where the material is prone to sensitization. This is front mein, whatever you can see is a nose, it is called as a nose. So as you can see here, in case of 0% cold work, the time required for the sensitization is slightly low as compared to for 10% cold work. You see the time required is approximately 0.1 hours. Within that particular temperature, if you take it to 1073 Kelvin, and within 0.1 hours, the material gets sensitized. So this shows that how sensitization is getting influenced by cold work. Apart from that, grain size also influences sensitization, and composition of a material also influences sensitization. How composition influences, as I have already told, because of sensitization, there is a formation of chromium carbide precipitate along the grain boundaries. And when these kind of sensitized material comes in contact with the environment, dissolution of these grain boundaries takes place, resulting in intergranular corrosion. So here, as we increase the carbon percentage, because carbon is one of the major which is responsible for sensitization. So when we increase the carbon percentage to 0.08%, the time required reduces. Similarly, if chromium percentage is increased, that means you're having a material which is having high chromium weight percent. So in that case, the sensitization is delayed because more and more chromium is available to stabilize the passive film, and hence it will the sensitization will be delayed. There are many ways by which in our labs we carry out these sensitization tests. So apart from that, there are some ASTM standards, which is A262 practice A to F. In this A262 practice A test is followed, which is the oxalic acid test. And these are all destructive tests. And if we want to avoid these kind of destructive tests, we can do ASTM G108, which is an electrochemical test, which is non-destructive. Little bit I will talk about what are the tests here. Okay, so now this is the ASTM standard with different test medium, and what are the features which we will see when after the test under optical microscopy. So when we do ASTM A262 practice A test, in this small coupons of the metal which is sensitized of our interest is taken. It is well polished, and then it is electrolytically etched in oxalic acid at a current density value of 1 ampere per centimeter square. And then the sample which is now polished will be seen under optical microscopy. We usually see these kind of structures. So this is one grain, this is another grain, and this dark line is a grain boundary. If the material is sensitized, we will see this kind of dark coloration, this ditch structure. Third one is it shows that material is completely sensitized. Why? Because when we are electrolytically etching the specimen, this chromium carbide which was there along these grain boundaries, they dissolve, resulting in this kind of black coloration. In this case, the material, in second case, the material may not be sensitized. Hence, because here some of the portions are showing light colored grains and some only are showing the dark because of chromium carbide dissolution. So this kind of structure is called as a dual structure, and this structure where you don't, all the grain boundaries are looking almost similar, showing that the material was not at all sensitized, or the yes. So that is important. Okay, so that is destructive. These kind of tests are destructive. Now, what is non-destructive testing is ASTM G108. Some of the conditions I have mentioned here. So we prepare these solutions at this particular temperature, and then electrochemical system is used for carrying out these studies, where potential is swept from 6 volt per hour. And here you can see this is the way it looks. So now this is a potential of the material. Now we apply a potential up to more noble side. So what happens during anodic, this is called as anodic. When we are applying a potential, the material starts showing this kind of high current. So wherever high current is there, that means there is more of electron flow. That means corrosion is taking place. And then it comes back to the passive state. And in the passive state, what happens? Chromium oxide, which is a passive film, again tries to form back. Then again, we do a reverse scan. So we go back like this. And if the material is sensitized, again in the grain boundary areas, we will see this kind of peak in current. So from this ratio of reactivation to activation peak, we calculate degree of sensitization, and based on these degree of sensitization, we evaluate whether the material is sensitized or not. Yes, now sensitization also can be avoided. Like if we have done some kind of welding or some kind of heat treatment on the material, what we should do is we should take these materials to annealing temperatures, which is 1050 degrees C. I have already told that sensitization takes place between 550 to 850 degrees C. But when we do annealing, which is at 1050 degrees C, the chromium carbide which was formed along the grain boundary, they all dissolve and they get evenly distributed into the matrix. So your grain boundaries are no more sensitized. That means we are avoiding sensitization. Many cases, as I have already told, carbon has a bad influence on sensitization. So we need to use low carbon stainless steel materials. Apart from that, we can use some stabilizers, and nitrogen. This L is low carbon, N is nitrogen. So nitrogen addition into the metal also has a very beneficial role. So we should use this LN varieties, and during welding, low heat input should be there. Okay, so now I talked about flow-assisted corrosion, pitting corrosion, crevice corrosion, intergranular corrosion. They are all problems which are seen in the reactors, can be taken care by doing many kinds of pickling passivation. This is another big problem, and my expertise is in stress corrosion cracking. So as the name says, corrosion is taking place when stresses are there. So you see, this is a Venn diagram which shows material. Generally, materials which we study is stainless steel material, and these materials in stress or strained condition. That means some residual stresses are there or some applied stresses are there. So material in stressed condition, when comes in contact with the environment, it undergoes stress corrosion cracking, hydrogen embrittlement, and corrosion fatigue. So these studies we carry out, and if the stresses are static, then material undergoes SCC, and if cyclic stresses are there, that means tensile stress for some time and then compressive stresses, it is in cyclic nature, then in that case corrosion fatigue failure takes place. This shows, see, here it is not a pit, here the cracks initiate and then they start propagating. So microstructurally, it looks like these kind of cracks with numerous branching. And here, this crack, you can see it is growing along the grain boundaries. These are called as intergranular stress corrosion cracking because it is along the grain boundaries. Now, these SCC problems are very severe because they are highly localized and highly branched cracks. There is no damage accumulation, which shows that when uncracked material is there and very next to it, if a stress corrosion crack is there, this uncracked material will have all mechanical properties in its good form. However, the cracked material will undergo a brittle failure. That means if ductile means you stretch, it will take some time and then only it will undergo failure. But SCC failure, just like a lead pencil breaking, just like a crack. So it is very dangerous, these kind of failures. And then it occurs in a material that show active-passive behavior, which I will tell why it takes place in those conditions. Then it also takes place below the yield stress. I already earlier I told, then when we are selecting the criteria for materials, we follow the design, we follow the codes. And in codes, it says that we can go up to the stresses of some value. And these materials can undergo failure even below those stresses. So these are very dangerous failures, and it takes place in specific medium. Now, what happens during stress corrosion cracking is, initially, the passive film which is formed on stainless steel undergoes breakage due to tensile stresses. So once the passive film breaks, material directly comes in contact with the environment, and then because of this interaction, there is corrosion which is taking place between the metal and its environment. And again, it has a tendency to repassivate metal, so repassivation is taking place. So when breakage of passive film, corrosion of metal, and repassivation takes place simultaneously, the material undergoes cracking, so crack initiation and propagation. Factors which influences SCC are tensile stresses, environment, temperature, alloy chemistry, and susceptible microstructure. So how tensile stresses will influence SCC? As the stresses are increased, its time to failure decreases for different kinds of metals, as it is shown here. And then for SCC to take place, strain rate is very important. So you can see when strain rate are very low, then there is only uniform type of attack will be there. And when strain rates are very high, then mechanical fracture takes place. So this range of strain rate, which is 10 raised to power minus 4 per second to 10 raised to power minus 7 per second, this is a range of strain in which material undergoes SCC. Okay, I already also told that specificity of the medium is very important. Now, for stainless steels, chlorides are the main cause which causes SCC. In this case, you can see why specificity is important. This is a metal. It is having a passive film. Now, here some defect is there because of which corrosion is taking place. However, this corrosion rate is very low. This kind of condition where currents are very low, material does not undergo SCC. In third stage, uniform corrosion will take place because so much of area is exposed. So this is a very localized form of attack, this second stage, where it shows that the current values are in a very narrow range, resulting in SCC. Now, so also you see, this is a range. As I've already told, this is a potential versus current density plot, and this is a S curve. So initially it has its own potentials, then there is a general dissolution, then passivity. So the region between general dissolution and cathodic protection is the range where SCC takes place. Then this zone where general corrosion and passivity is coming into picture, that is a second stage where SCC can take place. And zone 3, where from passive to undergoing pitting. So these are the places where the passive film which is formed on the material is not very stable. So in these cases, material becomes more prone to SCC. This this just simply shows there are different kinds of mechanisms by which SCC takes place, and it is dissolution controlled or hydrogen embrittlement. These kind of studies can be done in our labs and find out what particular material undergoes what kind of corrosion mechanism. Okay, so this just for information, the austenitic stainless steels which we are using for our reactors, the environment in which they undergo, and approximately you see most of the metals or most of the alloys undergo SCC in the specific environment of like for zircaloy, which is used in boiling water reactor, iodine, vapor, halides, methanol. In those conditions also they undergo SCC. So almost all the alloys undergo SCC. Only specificity of environment is important. Here, just for the information that chlorides, in the chloride environment, austenitic stainless steels undergo maximum SCC failures. And as I've already told that as the strength of a material increases, its SCC resistance decreases. Okay, so these are the different metallurgical parameters like cold work. Cold work is also, when we do cold work on the material, we introduce some residual stresses and increases the strain energy of the material. Also the defect density increases because of all these kind of defects present in the material due to cold working. SCC resistance decreases, yes. And similarly, if the material is sensitized, sensitization as such is a problematic case, and if the material is sensitized, then the material can undergo intergranular stress corrosion cracking. Even this shows for 316Ln base metal compared with of weld metal, and weld metal has inferior crack initiation as well as propagation rate. So welding also deteriorates the SCC properties of a material. This SCC can be avoided by appropriate selection of material. When we know that this particular material is prone to SCC in that environment, we need to replace that material with some other material which will not be prone to SCC, and then we can avoid crevices or artifacts in the stagnant water, and we can use better fabrication procedures to minimize the residual stresses present in the material, and then some kind of surface modifications so that the surface has very uniform passive fill, and like this then in case of stainless steels, low heat input welding procedures can minimize the sensitization. Chloride containing dye penetrant, it should be avoided when we are doing inspection. In those cases, what will happen if chloride is already there, then the material will start undergoing SCC. Pickling and passivation. So for most of the localized corrosion problems can be avoided if the material is pickled and passivated very nicely. Okay, now these are the corrosion problems of zircaloy, which is a boiling water reactor. So zircaloy is a cladding material. That means fuel is placed in this zircaloy. And zircaloy is, when it is exposed to water, it forms a passive film, which is ZrO2. Apart from that, it forms H2. This H, if we take the rate of reaction, different steps are there. First, H plus ions will form, then two H plus ions will combine and form H2, like this. So when these H plus ions are there, they go and sit into the metal because they are very small, and because of that, hydriding or oxidation kind of problems are there. And even in zircaloys, SCC takes place, as I've already told, in iodine vapor. So what happens is, this is a fuel. So here inside fuel is there due to sudden power ramps. That is, there is a rapid increase in the power. There is a failure. In case there is a failure here, so there results in the opening of this material, and this iodine vapor goes and sees the metal surface, which is zircaloy. And because of this, it leads to zircaloy SCC. This is one of the schematic which shows how the fractograph looks. And then this is another SCC problem in boiling water reactors where 304 stainless steel is used. So along the weld, this is welded area. And along the wells, you know that residual stresses are very high. So what happens when it comes in contact with the oxygenated water? Corrosion takes place. And these are some of the improvements which can be done. Too much details I will not. Okay, biofouling I wanted to tell, because of adhesion of so many types of microorganisms like microalgae or branchioles, oysters, these kind of bacteria, they come and get adsorbed onto the surface of the condenser material. And see here, this is the reason why the condenser material, this heat exchange capacity reduces and results into the failure. This biofouling can be avoided by chlorination or by sponge ball cleaning, by anti-fouling paints, or by different kinds of coatings, heat treatments, or control of flow of seawater. So now I will conclude that structural materials used in nuclear reactors have to satisfy some nuclear properties apart from strength and other common considerations. And this necessitates the use of special materials in the reactor. Presence of intense radiation fields of high energy particles, especially neutrons and gamma rays, which are present in the core of the reactor, induces microstructural changes in materials, which often will affect the corrosion resistance of the material. And also the corrosion in nuclear industry is that the cost of corrosion failure is many a times more than a similar failure in any other industry. Hence, this needs to be addressed. And this is a necessity for newer and better materials for higher design life requirements. This necessitates better R&D efforts in developing materials, and hence our data is given to designers, and they give corrosion allowance when they are designing for a particular material. They will give some corrosion allowance because of the information which we pass on to the designers. With this, I would like to thank all the listeners.
Thank you, ma'am, Dr. Anita.
Yes, ma'am.
It was a scintillating talk on performance.
Thank you, ma'am.
Environmental performance.
Yeah. Should I now show the...
Thank you for your scintillating talk on environmental effects on the performance of nuclear material, ma'am.
Yes.
Ma'am, I request you to share the quiz for the short time teaser. So
Yes.
in this regard, the participants are asked to post their answers in the chat box, and also the participants who are watching in YouTube stream can post their answers in the comment box. And please, ma'am.
Okay, sir. 1 second.
Okay. Please share the questions, ma'am.
Yes, sir.
Okay.
Yes.
Full screen. Okay. Please make it full screen. Okay, fine, ma'am.
Okay, so my first question is, wall thinning of carbon steel material takes place due to 4 options are given.
The first question is wall thinning of carbon steel material takes place due to option A, pitting corrosion, option B, uniform corrosion, option C, microbial corrosion, option D, crevice corrosion.
Yes, sir.
Yes. Second question is the stress corrosion cracking is a form of dash. Uniform corrosion, localized corrosion, mechanical failure, and D, fourth one, none of the above. Third question, unit of corrosion rate is A, micrometer per year, B, gram per cc,
CC.
mils per year, both A and C. I request the participants to post the answers in the all the 3 question answers in the single chat box, like 1 B, 2 C, 3 D, like this. Participants are posting their answers. I request the participants to post their answers in the single chat box. Dandabani, Lata Madam, Rinatson, and Sriti Biju Kumar has given their answer. Let me see whether it's right or not.
Yes, sir.
And some more participants are posting their answers. Nandini Palanichami Madam, Chitra, Srilata Mimidi, Geeta, Ram Kumar, and NP Ramesh, Reena Saro John, Sriti, Lata Abhishek, Chandrapriya, they are posting the answers. I request all the participants to post the answers in the chat box. We have 2 more minutes. Participants, please post the answers in the single chat box. Yeah. Now the participants are posting their answers in the chat box.
Yes, sir.
Yes, ma'am. You also see the chat box, ma'am, Anita, ma'am.
Okay, I will just.
No problem, ma'am. Okay, I'm seeing here. Just okay, I'm asking you, ma'am. One more minute. I request all the participants to post their answers in the chat box. Let me see how many have given the correct answers.
Yes. Should I go to next slide?
Yes, ma'am. Please, show the answers, ma'am, so that the participants can justify their answers.
Okay, sir.
Okay, fine. Thank you, ma'am. Please go to the answers.
Yeah. Yes, these are the answers.
Wall thinning of carbon steel material takes place due to answer B, uniform corrosion. The second question is stress corrosion cracking is a form of dash. Answer B, localized corrosion. And the third one is a unit of corrosion rate is both D, both A and C.
Yes.
Thank you, ma'am. Now, I request the participants to raise their hands for the interactive session.
I can stop sharing now?
Yes, ma'am. Yes, ma'am. You please, okay, stop share. Now, I request the participants to raise their hands for questions. Few participants are raised. Ratika Komalam, madam. Please unmute yourself, ma'am. Ratika Komalam, madam. Please unmute yourself over there.
Sir, hello.
Yes, ma'am. I able to hear you, ma'am. Please ask your question to Dr. Anita Thopu, madam.
Sir, so in the +2 level, how can I help my students regarding different materials that are used in nuclear reactors? Because in the +2 level, we have to learn the diagrammatic representation of a nuclear reactor and the smallest details on how a reactor works and the different reactors in entire India. So to what level can I talk to them?
Anita ma'am, please.
Yes, this is a very good question, ma'am, because nowadays I feel in +2 level they have mechanical properties of material as one of the chapters.
Yeah, in the standard 11 they have mechanical properties of fluids and solids.
Yes, I mean, in these conditions, you can talk to them about the mechanical approach as well as the types of corrosion. Actually, corrosion is there in their syllabus by any chance?
In chemistry, they have, ma'am, not in physics. But in nuclear reactors, there are many children who are really very interested in nuclear physics. So we are also limited by our syllabus. We give a schematic diagram and we explain how a reactor works, how a thermonuclear reactor is like.
Yes, yes. Because I also remember in my 12th, I have studied something about radiochemistry like that.
Yes, ma'am. Actually, if we can say more about how it really works and how I can help them to motivate, to read more about it. If you can give me a small insight on a +2 level, how can I, as a teacher, I can help those children?
Yeah, actually, see, that is why my first initial 2-3 slides were on boiling water reactor, heavy water reactor, and fast breeder reactor.
Yes, ma'am.
So those kind of slides, if some kids are interested, you can make those slides. I mean, if you need our help also, we are there to help you.
Yes, ma'am.
From those, you can explain what are the materials and what are the corrosion problems related to these materials.
Okay.
It will be nice, ma'am. Actually, kids should get interested in these fields. And I also wanted to tell, see, I did my MSc from university. So many kids know after 12th, they can go for BSc, MSc, and then become nuclear scientists.
So, ma'am, actually, there are many children who are interested in taking BSc Physics and pursuing their course in physics.
Yes.
In fact, after listening to the initial talk, only I could understand that so many, places are there where
applications.
Studying. Yes.
So that is why I wanted specially to tell that after doing BSc, MSc, also these kids can come into as a nuclear scientist in our department. It is very much required. We need so many scientists here.
Okay. Thank you so much, ma'am.
Okay, ma'am. Thanks.
Thank you.
Thank you, Radhika Komal, madam, for your active
participation. Thank you, sir.
The next participant, Reena Sarah John. Madam, please unmute yourself. Reena Sarah John, madam. Please unmute yourself. You raised a hand. Reena Sarah John. Madam, please unmute yourself, madam. Reena Sarah John, ma'am. Ma'am, there are some questions the participants asked in the YouTube streaming, ma'am. Can I, ma'am?
Yes, sir. Yes, sir. Yes, sir.
Manimaran Kandasamy asked, is liquid sodium made any effect on cladding when we are using it as a coolant?
Yes, actually, this is another very interesting question. I liked that they were listening very carefully to me because I did not tell about any corrosion problems with liquid sodium. See, here the cladding material which is used in fast breeder reactor is alloy D9 or type of 316 stainless steel. And the liquid sodium is a metal. So generally when metal comes in contact with these kind of stainless steel material, there will be no passive film present on the material. And generally all the corrosion problems are because of the passive film which is present on the material. Because of disruption of passive film only these kind of corrosion problems takes place. But once liquid sodium comes in contact with the material like 316 which has passive film, this passive film gets dissolved into liquid sodium. So there is no passive film, there is no corrosion problem as such. But now 316 Allen stainless steel also is an alloy and sodium is a metal. So there are other kinds of problems like both of them get melted together. Those things don't come into corrosion, but other kinds of problems are there, but not corrosion problems. I hope I clarified.
Yes, ma'am. Thank you. Thank you so much for your the detailed answer, ma'am.
Okay.
And the next participant, Mr. Praveen, please ask. Please unmute yourself, Praveen. You can ask your query. Praveen.
Yeah. Yes, sir. Good afternoon,
yes.
ma'am.
Good afternoon, sir.
Yeah, ma'am. What are the safety measures taken in case if there is any failure in the nuclear reactor? Because it is also an interesting study to work with.
Yes, yes, yeah. So actually, there are what schematic I showed. There are containment buildings. There are so many lead shields. Actually, if there can be a visit, I mean, I don't know. It will be nice. Those people who are interested can come and see our reactors and see how safe our reactors are to be operated. We have lead shieldings. We have containment building, and all safety measures are taken so that there should not be any problems in many cases. No, see, this doesn't undergo any kind of what do you call seismic problems are also not here. Earthquakes and all that doesn't take place here, but even those considerations are taken, and with those considerations our reactors are constructed and they are absolutely safe. And apart from that, we have safety grade decay heat removal system, so that if very high heats are produced, there are decay removal heat systems are there which will absorb all the heat. So any kind of catastrophic failure is not possible in the reactors which are there in India.
Thank you so much for your detailed answer, ma'am. Mr. Praveen, do you have any more questions? Praveen, Mr. Praveen, are you there? Please unmute yourself.
Yes, sir.
Yes,
Sir,
do you have any more questions?
Yes, ma'am. We are preventing against natural calamities, seismic activities. So,
Yes.
what's the case in case of any fauna attack like locust infestation or any other microorganism entering the containment zone? Is there any safety in prevention methods for that?
Actually, locust and all that is not a problem in our reactors, but there are absolutely no problems, sir. That much I can assure as a nuclear scientist working in our reactor. I have seen because so many Chernobyl accident was there outside, not in India. So many other places, so many problems were there. 3 Mile accident was there. We have like Fukushima was very recent, which happened. We have gained experiences from their failures or disasters, and all those kind of things we are taking care in our reactors and in future reactors. So far, we have not faced any kind of these kind of disasters. So it is taken care of in India.
Okay, ma'am. Thank you, ma'am.
Thank you, Mr. Praveen, for active participation. And again, Radhika Komal ma'am raised her hand. Ma'am, please ma'am, please unmute yourself, ma'am. Radhika Komal ma'am, please unmute yourself and clarify your doubts, ma'am. Radhika Komal ma'am. Okay, ma'am. So one more, few more questions from the YouTube streaming, ma'am. Can we use airflow as a coolant? How effective will it be? Praveen asked the question.
For fast breeder no, see, there now coolants also, whatever we are using is we have selected based on so many categories and so many criterias, and the heat transfer capacity of this air. See, for our reactors, no, heat transfer capacity should be very high. Then only whatever fuel, whatever energy is produced can be converted into electricity. But this air is having a very low heat transfer capacity. So if you use air as a coolant, then it is not efficient. The efficiency of the reactor goes down. So we cannot use heat as a air as a coolant.
Okay, thank you so much for your detailed answer, ma'am.
Thank you, sir.
One more question, ma'am. Because of corrosion problem, we are looking for a new types of materials. So in in the same track, can we looking for a new types of coolant or moderator instead of water and wax? And can you give us an example?
Okay, now see, moderators are required for light water reactors. Now we are trying to go for fast breeder reactors, because initially Parmeshwaran sir told there are 3 stages. First was the light water reactors. Then we are in a second stage where is fast breeder reactors. So apart from liquid sodium, lead is also used as a coolant, not as a moderator. Moderator was used in the first stage, as well as in the third stage it will be used. But apart from liquid sodium in the second stage, lead bismuth also can be used as a coolant, but then there are so many problems. I mean, research studies are going on, and so we are presently sticking to liquid sodium as the coolant.
Thank you, Dr. Anita Topam, ma'am, for your wonderful answers for the participant question, ma'am. Thank you so much. Now, I request Dr. Karthik sir to share the permission PPT. Karthik sir. Karthik sir. Yes, Karthik sir has started the screen sharing. Yeah, now it's visible, sir. Very fine. I request the permission, sir, to continue his session, sir. Dr. Permission, sir. I hand over the session to you, sir, please. Permission, sir. Please unmute and you can start your presentation, sir. Permission, sir. Are you able to hear me, sir?
Sir,
permission, sir. Able to hear me?
Sir, I am checking. Sir, I think sir is not here.
Sir is not here. Permission, sir. Okay, please check, sir.
Sir, okay, sir is now co-host. Sir, unmuted yourself, sir.
Okay, now I'm able to. Yeah.
Yes, sir.
So where I left is the world scenario about the electricity production is around 11%, with the US about 100 reactors, and there are nations which are France, Lithuania, Slovakia. They have their own 100% electricity from what we generate from the nuclear power plants, only about 11.2%. But the world, from 3 countries, they are able to generate electricity from nuclear power fully. Let me go to the next slide. Karthik will help.
Yes, sir. Karthik, sir. Please go to the next slide, sir.
Karthik,
sir, able to hear me, sir?
Yeah, go ahead. Yeah, go ahead. I have slided. Yeah.
Yes, sir. Yes.
Slide?
Yes.
Yeah, you are able to see the slide. Yeah,
yes,
I'm able to hear you. I have got past.
Okay, fine, sir. Thank you.
so as far as the nuclear energy option is concerned, the reason why we have Karthik.
So Karthik, sir, you please share the screen, sir. Karthik, sir, you please share the screen, sir. Karthik, sir.
Yeah.
Okay, fine. Please make it full screen, sir.
So if you look at
yes,
the energy that is produced from elastic deformation, it will be at the bottommost, and 1 degree of temperature change of water is actually 1 joule or 1 BTU per pound. And oxidation level, you generate about 10 power 4. If you look at fission of uranium, you generate about 10 power 10. So it is about million times better energy that is being released when you burn, when you fission uranium compared to what you generate by burning carbon or coal for that matter. So the tremendous advantage uranium gives or the nuclear energy gives is million times better than coal. That is a fossil fuel. On the right side, you find two important pictures. One is a symbol of IRE, Indian rare earths, and beneath the Kerala beach sand, presence of monazite, which is rich in thorium. This is very important, and these two give a strength to our nuclear program. As I progress in the next slide, I will discuss more about it. Go to the next one, please. Uranium is an efficient energy source. This is what I said. If you see this picture clearly, 5 fuel pellets of uranium is sufficient to generate 1 year of electricity for a household need. If you compare this with oil or coal or natural gas, you see on the right side 149 gallons of oil and 1,780 pounds of coal, and in terms of natural gas it is 17,000 cubic feet. So this is the consumption, whereas we look at the pellets, it's very, very small, and it's only 5 fuel pellets. So that means the energy source where uranium is very efficient. This is the first advantage. Next one. Next slide. In portraying the same idea in a different fashion here, you could see that the picture clearly shows a huge amount of coal or a huge amount of oil and huge amount of mineral oil in comparison to natural uranium. The sentence what it reads is that with a complete combustion of or fission, 8 kilowatt hour, that is 8 units of heat is generated from 1 kilogram of coal. It is 12 kilowatt hour from 1 kilogram of mineral oil, whereas the same amount of uranium provides 24 million kilowatt hour. So that is the amount of advantage we have. That's why million times advantages is uranium fuel. Next one. Karthik, can you move?
Karthik sir, could you change next slide, sir? Karthik sir. Karthik sir, able to hear us?
See, I have already slided. Next slide. I have already. Yeah, I'm able to hear you. I have already gone to the next slide. It is.
No, sir, it's not changing over here.
Probably you move like this, yeah. No problem. So the second reason is why nuclear option for energy security is that the fossil fuels are dwindling. Maybe in another 100 years or 50 years, we will run short of coal, oil, and gas. Therefore, this is the second reason uranium is available, and there is also possibility that you can breed new material, nuclear fissionable material, and these two things made that we can have a 3-stage program which can take us for the next 500 years. So that is the second advantage. Next one, please. And the third advantage is nuclear energy is green energy. You can see the rays, solar is green, but solar preparation requires reduction of silicon dioxide with carbon, therefore it is not considered. It leaves a footprint. You can see the footprint left by the solar fellow. And if you look at the footprint of fossil, it is well known, whereas wind and nuclear are in the race as a green energy. Third advantage. Next one. In comparison, this slide supports the previous slide that the amount of coal required is about 380,000 tons per year. Whereas if you look at on the right side, it is very less, and 12 tons of uranium per year. If you look at the SO2 release or the CO2 release, 15 tons of CO2, 1 ton of SO2, NO2 also is released. Ash, 30 pounds of ash. All these things are not there. And I will not talk about the rest like death and other things for the time being. Let me move to the next. In this slide, I would leave the top portion. The bottom portion, I have underlined one more advantage, that we have thorium on the beach of Kerala, which can convert itself into uranium-233 if you put it in a breeder reactor. So that is our third stage, uranium-233 as a fuel. In the second stage itself, we will present uranium, natural resources, which is converting itself into plutonium, and thorium into U-233, and these two will serve as a future fuel. And therefore, this is the fourth advantage why India go for nuclear. Next one. If you look at the composition of the naturally occurring uranium, the isotope 238 is dominant, 99.3. If you look at 235, it is the fissile one, is 0.7. That means what? Fertile means it cannot be fissionable. Fissile means it can be breakable or fissionable. 234 isotope is very, very minor. That is 0.005, negligible. And if you see the reactions beneath, uranium-233 can be produced from thorium, because it is when one neutron bombards the 232, it converts into 233, and this is man-made fissionable product which will serve for the third generation of our reactors. Plutonium-239 is produced in our natural uranium reactors as well as the breeder reactor. Breeder reactor breeds faster. So 238 isotope, when it gets one neutron, it converts itself into neptunium and then finally end up in a plutonium isotope. And this is man-made first isotope, and this serves our reactors of the second stage as well as the third stage. Next one. Current status, if you look at it, we are making 4,780 megawatt of electrical through various reactors at different places, which I will touch upon later. We are planning to build about various reactors. Next slide will show. We want to go up to 500 gigawatt nuclear capacity by 2060. Let us see, we will achieve. And nuclear energy is expected to provide half of all our electricity. That is what we say. Next one. These are all the places: Narora, Rajasthan, Kakrapar, Tarapur, Kaiga, and Madras. So these are all the places Nuclear Power Corporation (NPCIL) has built pressurized heavy water reactor (PHWR). This is natural uranium with heavy water as the coolant, as established already, and they are giving around 4,700 megawatt electrical. Next one. The next slide shows various places where we have Department of Atomic Energy has started reactors building, and Kudangulam is already ready. We are using it, and this is the pressurized water reactor. Kalpakkam we have already running, and you see on the Andhra there is a reactor planned 1,000 megawatt, 6 units are planned. Madhya Pradesh, and so also various places throughout India. And what is available is Kaiga, and all these places are already only our pressurized heavy water reactors. And except Kudangulam, all others are pressurized water reactor. Tarapur is the first reactor. which is BWR, boiling water reactor, and Kudangalam is pressurized water reactor. Next one. So whatever I said is that Tarapur, a boiling water reactor, is built with the help of with USA, and this was in 1970. So by 73 we had interaction with Canada, and the CANDU based uranium, natural uranium heavy water reactor was built. France helped the initial stages to build a fast breeder test reactor, that is FBTR, which is inside IGCAR, doing some testing of fast reactor materials, all these experiments. And now POBR, which whatever we have built, is ready for commissioning. On the right side, you find PWR with the Russian help in Kudangalam. Next one. So this is the schematic of CANDU reactor, which was Canadian deuterium uranium reactor CANDU, which is basically shown here. And next one, next slide, shows why reprocessing is an essential step. After the mined and enriched plant provides the uranium, which is put inside the reactor. After reactor is using it, we will have to reprocess the material to get the uranium plutonium fission products, and which can help us new fuels, and some of the things can be used as medical also. So therefore recycling is a very important process in our department, and therefore chemistry, chemical engineers do have excellent opportunities. Next one. This is the second stage initiated after FBTR had done excellent work, and this is located inside our center, and this is doing a lot of experiments since 85 when it was gone into critical. The next slide will show you the initial stages of 500 megawatt prototype fast breeder reactor, again in Kalpakkam, but it is under a separate corporation that's called Bhavini, and now it is completed. What the picture shows is the initial stages of excellent mechanical engineering work of installing the whole reactor, and that's what you are seeing. Now the reactor is ready, and at any stage it will go into commissioning. Next one. So that way we have crossed first stage, and second stage is almost imminent. And once we are getting thorium converted into uranium-233 through the breeder action, this can be used in the third stage of Indian nuclear reactor. Therefore, that is the third stage of our reactor. Next. So that way our visionary Baba thought about this for India, and the next 500 years we should not have any difficulty in power. And this is a very good animation where the pressurized water reactor present in Kudangalam is shown how the heat that is generated is taken in by that water that is circulated in the steam generator, going into the turbine, making the generator rotate, and hence generate electricity and supplying it into the city, and city lights are burned. And of course, the water from the turbine returns back. The steam is converted, cooled or condensed by seawater, taken back into the steam generator again. An excellent animation. Next one, please. So the various types of reactors, if you look at the world over, the heavy water is about only 5%. But if you look at the pressurized water reactor, the previous slide, whatever I showed, is about 57%. And boiling water reactor, about 31%, other reactors 1%. But we are with a lot of heavy water reactors, and pressurized water reactor is only one. Okay, and boiling water reactor only one. Gas cooled reactor we are not using. It was initially built by US. Next one. And globally, as I have mentioned, India is producing only 0.5% compared to all other developed countries, economic cooperation and development, those organization countries, and mutual economic assistance, like the council, those countries, USSR, Germany, all those things. Next one, please. And the two difference between the thermal reactors, why we call thermal reactors, the pressurized heavy water reactor located at Kalpakkam, Narora, all those places, the 5 places, is sustained by a neutron whose energy is 0.025 eV. That means it is thermalized. So that's why called thermal reactors. It uses a moderator, that is the heavy water, and reduces the energy from 1 MeV to 0.025 eV. Therefore, increases the chances of fission. On the other hand, on the right side, the fast reactor, the BTR and PFR use 1 MeV neutrons and there is no moderator. So this question is very important. Moderator is not present for fast reactor. Okay, next one. Next slide, please. I would answer all the questions at the end, please. And if you look at what is fission, fission is a very important reaction. Neutron is essentially to be produced. How do you produce neutron? Beryllium and boron. These two, if they are bombarded with alpha atom, alpha producing atoms like americium, all those things, it can generate a neutron. This is called a transmutation reaction. On the right side, you find there is another method. If you impinge or shine gamma, the gamma, when it interacts with deuterium, that is the hydrogen isotope, it can generate a neutron. Or beryllium, when it is bombarded again by gamma, can generate a neutron. So these are the two ways by which neutron is generated. The animation shows how the neutron bombards a uranium heavy atom, and there are 3 more neutrons are generated. So this is very important, and there is a very important diagram for the nuclear physics. I'm not touching upon. That shows that above iron in the atomic, if you plot the atomic number versus the binding energy, the atoms are becoming very easily fissionable when you go to the higher level of atomic number. So uranium is one such element. Next one, I also shown on that same picture Enrico Fermi, who is the first person to build the first reactor at USA. This reaction shows how a sustained power is possible using a nuclear reaction. When you bombard uranium by a neutron, you generate 3 neutrons. These 3 neutrons will again interact with 3 more. So like that it generates, and therefore a sustained chain reaction, which is shown symbolically at the right side bottom. So chain reaction is a very important term for you, and this is what sustains, and it should be controlled. If you do not control, it can go into a bomb. Next one. So now, so far what I have spoken is about an introduction to the Indian nuclear program. Now the material selection. This question was thrown to my previous speaker, and to a certain extent, I think I would cover this alone. Next one. Materials we are today, what we discuss here will be solids, and solids are stable. As you know, somebody is solid. A solid body means that nothing will happen, but they do degrade. Solids degrade over a period of time. That is called evolution in its properties. Or if you beat the solid, for example, a goldsmith beat the gold, there's a changes in the property, it will break after some time. So therefore, a processing of annealing followed by beating of the gold is very essential. A glass is totally different from a steel. A cube of steel or a cube of steel and a cube of glass, if you compare, glass will break when you drop it onto the floor, whereas steel will not. Therefore, the properties are determined by how the atoms are placed inside the various positions in an atomic level. Therefore, a structure, what is called microstructure, is very important. And by understanding microstructure, you will understand why a glass breaks, why a steel doesn't break when it's dropped. So therefore, the selection of materials essentially require understanding of the properties in terms of the structure. That's why called structure property correlations. Next one. So in this domain, you can have a material science person understanding the chemistry as well as physics. And here I have shown you that inside the reactor, when you place any material, it gets continuously bombarded by neutrons, it breaks, and therefore you find a lot of changes that is happening. And that is what is shown here. A little bit I will show in the next few slides. Next one. It is like a carom board in which when the neutron bombards continuously, you get a lot of changes or displacements. I use the word displacement of the atoms to inside positions called interstitials. As a result, if some atom has displaced itself, that place become a vacancy. So you find point defects, that is zero dimensional defect generated as a function of these displacements. And next slide, please. And this again a schematic. When these displaced atoms come together, they can form what is called a precipitate of impurity atoms, or it can be a self-interstitial, that is a position which is not actually allowed, but it is sitting, or a small atom which can sit in a position interstitial impurity atom. Suppose the whatever the vacancy you have generated, they all go and form together, then it will be becoming what is called a round wire, which will be of the order of nanometers. Whatever the displacement of an atom is only an atomic level, Armstrong level, whereas when they are together, they become a very wired, and which is about nanometric level, 20 nanometers, 30 nanometers. I can show all these things later on. And they also can form what is called a one-line defect, that is called dislocation. Very important invention, which is for the deformation people who try to deform metals. It is very important. Is the dislocation which is being deformed, and sometimes a three-dimensional precipitates can form. Sometimes a three-dimensional impurity can form, which is again for spoiling the mechanical properties of the materials being employed. Next slide, please. So whether we can see really these things, yes, it is possible. Through transmission electron microscopy, one can see the dislocations, one can see a wire. So what is the great importance? When these things become more, the strength of the material will go high. On the other hand, the toughness of the material will go down. Toughness means, okay, for the time you can think ductility. So what will happen is, as a goldsmith beats the gold, after some time it becomes brittle. That's why he will ask his son to put it in a fire to anneal out. The same thing happens here. The material becomes brittle when it started increasing in its strength and losing its ductility. That's what is happening. Next one. Next slide. So this picture shows on the right side the dislocations which are shown as a line defect, a very important phenomena. And this is the defect, line defect, very much responsible for all the deformation that the goldsmith does, or the people in NFC, nuclear fuel complex, draw a tube or make a forging, everything. Okay, next one. Next slide. So advent of the nuclear energy also provided the chemistry people with a lot of opportunity. New periodic table elements were found out. First one is the plutonium. And I have listed C. Bohr as the father of nuclear chemistry. C. Bohr is the person who did a lot of research and found out many nuclear materials, many metals in the periodic table. And in fact, an element has been named after him, is called C. Borgium. Fermium, named after Enrico Fermi. The picture of Fermi is shown in the beginning. Rutherford, you all know, the scientist from New Zealand, and he is the father of atomic energy. Atomic physics rather. Rutherfordium, borium. Borium is again Bohr, Niels Bohr. And we can have generators, accelerators, where electrons are driven to high energy. BECC Calcutta, one can go and work there. Variable energy, cyclotron. Bose-Einstein statistics is very important because Bose, who lived in Calcutta, contributed along with Einstein for the thermodynamic statistics. Homi Bhabha, the father of atomic energy. Yeah, once again, his birthday falls on 30th of October. Every year it's being celebrated in a very good way. And this way we should remember such a nice visionary who has contributed for the Indian nuclear program. Next slide, please. This periodic table consists of all the elements. I have rounded Rutherfordium, Seaborgium, Borium, and on the right side I have put a vacant space where you find that fluorine, chlorine, bromine, iodine, and the next one is actually radioactive. Please click. Next slide. Next slide. So this is the astadine. The element is again falls in the same group. Next one is isotope, which is radioactive. Next one. So now going into the primary components of a reactor, the fuel, you have two elements, uranium, plutonium. They undergo fission easily because uranium is 235 and fissionable, plutonium 239, that also is fissionable, energy is least. So that's the most important criterion. Structural element, aluminum, stainless steel, zircon. This is all the tubes inside the fuel pellets are stacked. Okay, we use zircon for the heavy water reactors, stainless steel for the fast reactors. Okay, moderator, that is to slow down the energy of the or reduce the energy or slow down the neutrons. Light water heavily does that. Heavy water is good, so PSW use that. Graphite is also a very good moderator. Beryllium is also a moderator, but beryllium is toxic. Slows down the neutrons, 1 MeV to 0.02 eV. Reflector, very important. In the fast breeder reactor, blankets are used, and this will reflect the neutrons back into the system, and they don't want to allow neutron to go out of the core. And blanket is basically depleted uranium. That is, uranium is depleted of the fissionable material, that is U-235. The rest of the element, that is 238, which is 90, almost 97.7. Therefore, that can be completely converted into plutonium. And thorium is very important. The beach sand of Kerala contains this. If you put thorium, it will convert itself into 233. Therefore, they form the new fissile material for the next few hundred years. Control element very important: cadmium, boron carbide, hafnium, gadolinium, boric acid, silver, indium. Among this, cadmium and boron carbide we are engaging. Cadmium for controlling, that is, the criticality should not be crossed too much, power should be maintained, and there should not be any bomb explosions. And therefore, cadmium for thermal reactors, that is the PHWR, boron carbide for fast reactors, and cool and light water reactor for pressurized water reactor, heavy water for pressurized heavy water reactor, CO2 for gas cooled reactor. I think UK does that. And helium, those things are costly. Liquid metals is very important. Sodium, potassium, lead. We are using sodium, and I will talk about it later. It takes the heat from the core and go exchange with water, and water will convert itself into steam, steam goes to turbine and generates electricity. Shielding is very important. Lead is a very good shield. Steel is a shield. Concrete is shield. Water is a shield. That is to protect the personnel from getting radiation. Next one. I think this slide also answers the question asked how the students can be taught to my previous speaker. So how do you select? What is the parameter? To select the material, cross section is a very important physical parameter. Suppose how do you count the money in terms of rupee or paisa? In the same fashion, cross section is an important parameter. Next one. The next slide shows what is cross section. The definition of cross section. Cross section is what is the interaction of the neutron with the atoms. So therefore, the cross section should be in terms of area. And the cross section are different types. It can be absorption type. It can be a cross section, scattering cross section. So I will talk about this as I go into the next few slides. Next one. The nuclear radius is of the order of 10 to the -12 centimeter, very small. So if you multiply that by r squared, it is 10 to the -24 centimeter square. So this is the unit, is called bond, and therefore this cross section is used to understand the selection of materials. If it is an absorption cross section, it should be very high. It should not be one bond. It should be around few thousands of bond. For example, a material like cadmium, boron. Whereas a moderator should have very less bond. That is, the cross section should be low. Next one. So in this slide gives clearly what a fuel should have. The most important thing is fuel should have more amount of fission atoms. For example, uranium fuel will contain, if it is enriched, it will consist of very high amount of fissile atom 235. But at the same time, it should have high melting point. It should not become molten quickly when the heat is being generated because of fission. It should be also radiation resistant. It should not slowly change into its shape and give troubles. It should be chemically resistant with heavy water or water, and it should be easy to fabricate and high thermal conductivity so that it can transmit the heat. Else it will be at a particular location, it will become bulged. If you look at the moderator, it's generally, I have listed graphite, water, all these in a low mass number, that is atomic number is low. It should have high scattering cross section. It should not absorb, and that's why low absorption cross section. Compatibility with the materials we have engaged. I think this question was posed to Anita, that whether sodium is compatible with stainless steel. Yes, it is. Very good. But if it becomes sodium oxide or hydroxide, caustic embrittlement or stress corrosion cracking is what she has spoken. And the moderator should not become active. That is, activity means it should not become radioactive. It should be available cheaper. I think water is available. Heavy water is also, we are good. India is #1 in the world in producing heavy water, and it's doing very well. If you look at the next one, coolant should be, specific heat should be high, so it can absorb maximum heat. High boiling point. In this respect, sodium is very good. Boiling point is 900 plus degrees Celsius. Melting point is 90 degrees Celsius. High thermal conductivity, very good. Small neutron absorption cross section should not eat away the neutron. It should allow the neutron to allow. Low induced activity. It does not become active. Okay, sodium 24 can form, but not too much. Cheaper, it is available. And if you look at the control element, good dimensional stability, very important. Good thermal conductivity. It will be going inside the reactor only to prevent the reactor from going into a bomb level. So, or when you want to shut down, you require the neutron capture is more. So you insert the thing. Till then, it will be remaining dimensionally stable. Thermal conductivity is high. It is not getting corroded. It is easy to fabricate. Boron carbide is very good. Cheaper. Structural element, all should contain good strength and ductility, impact strength. I think Dr. Karthik will speak at length on these things. I will go to the next slide. Next slide, please. So if you compare for fuel, uranium in two different forms, one as oxide, one as carbide. Its melting point wise, 2800 for oxide, 2300 for carbide, good. Density wise, it is 10.95, 13.63. That means it has got more amount of porosity. Thermal conductivity is okay, 0.03 and 0.25. Uranium carbide is better. Specific heat wise, 234 joule per kilogram per Kelvin, 200 joule per kilogram per Kelvin uranium carbide. Both are equally good. Structure wise is good. If you look at the number of uranium atoms, 100% in uranium means in oxide it is 51%. If you look at uranium carbide, it is 95. That's why carbide fuel is better. Our world over uranium oxide has been employed. Therefore, it is considered to be the best fuel and for our reactors. Next one. If you look at what is the procedure by which we are doing this, the pitch blendy, the uranium ore is mined and then it is taken out and milled and it is converted, and slowly it is converted into what is called UF6 into yellow cake. The ore is converted into yellow cake, and the yellow cake is taken out and converted into uranium fluoride, and then it is separated out in two different forms, finally converted into oxide, to which goes into the reactor. Okay, next one. And whatever we are speaking, all these things are done here. Nuclear fuel complex. You can see this picture shows the yellow cake made from natural uranium is being processed in a massive mill in Jadavguda in Jharkhand. And this is the yellow cake. Though it is it's yellow cake, because of the nature color, it is yellow cake. And this is used as the initial starting material to prepare our uranium oxide. Next one. This compares the canning material or the tubes. I have already mentioned aluminum. I also mentioned zirconium and stainless steel. I have highlighted zirconium and stainless steel for our reactors. Next slide. The role of zircala is the most important thing. Instead of zirconium, which is easily attacked by water, we are adding a little bit of tin to make 1.5% of tin to make it corrosion resistant. The mechanism of corrosion is given. For want of time, I will not go into this, but you assume that this nitrogen which is present in the atmosphere also can give a trouble. Therefore, when this tin is added, tin will neutralize the effect of nitrogen, and therefore the corrosion attack is equally stopped. Next one. There is still another problem, what is called a little bit of course, you cannot completely eradicate the zirconium getting oxidized when it interacts with the water or heavy water, and therefore there is a possibility of hydrogen production that is up to about few hundred ppm, and this is in high temperature 350 degrees Celsius in the natural uranium reactors. PHWR is there. However, we do not want this. When the system is shut down, it will actually precipitate, because room temperature zirconium cannot hold not more than 0.05 ppm. The hydrogen will come out as hydrate. This hydrate travels. So our mechanical engineers along with metallurgists have developed a very beautiful program in what is called pilgering, and this processing of the zirconite tubes in nuclear fuel complex Hyderabad has successfully done away with this problem of hydrates. And you can see in the next slide what is called orientation of the hydrates, which are basically circumferentially laid. How this is possible is by pilgering process. A schematic is shown on the top left. You can see that two rolls are rolling and the tube is being manufactured, which is also rotating, and therefore this process makes the hydrate which later on when the tube is in service to precipitate and in the form of circumferential hydrate rather than radial direction. If it forms radially, it will break into two. Therefore, the metallurgists have played a very important role by understanding the texture. I use a term called texture, and this is a very important aspect of physical metallurgy. Next one. Irradiation on mechanical properties is very important. Dr. Karthik will conduct on this at length. Only I would say touch upon quickly saying that, as I mentioned, when the material is inside the reactor, the tensile strength is increasing continuously. This picture shows the stress strain diagram. I think 10th, 11th students will know this. Hooke's law, all those things they would have read. An unirradiated material shows a beautiful curve, a broad curve with good toughness, whereas when it goes to 10 power 19 or 10 power 20 neutrons are bombarded, the whole thing is strengthened like anything, but the ductility has gone down, or the toughness, the area under the curve has gone completely down. Further, you will listen to Karthik when he talks about this. Next one. Next one. Next slide, please. Yeah, there is another important property I mentioned initially about impact toughness. That also is very important for our material. So this also our Dr. Karthik will speak. I would also highlight very important thing. This you leave it, Karthik. Next one. Next slide.
Karthik sir, please move on to next slide, sir. Karthik sir, please move on to next slide. Thank you.
Yeah, void swelling is very important. Our mechanical engineers speak at length. I think in the initial slides I was told about some 10-20 nanometer size round voids, which can be seen only in microscope. But they use this word void swelling quite easily. And as the material gets irradiated, the strength increases, ductility decreases, and this is due to the defects accumulation. This void also accumulates. Vacancy generated that agglomerates to form voids. And about 5 to 10% swelling is sufficient that the material, the tube, the can material will become bulged. It will be a problem for the mechanical engineers to take out the fuels after irradiation after 2 years rather. So I will show how the voids look like in the next slide through the microscopy. And before which I wanted to tell what the mechanical engineers generally find it difficult. That is the tube which is inserted carrying the fuel is become a bulged, or it can become a change in its dimension, bowing or dilation. These are all the problems mechanical engineers highlight, and they say immediately it is due to void swelling. To see a void, you have to come to me and I can show how a void looks like. Next one. This shows a picture where on the left side, a completely initial material consists of a cold work material without any voids. On the right side, there are two pictures. One is a low magnification picture, shows round white dots, which are nothing but wires. Why wires are white? Because the electrons pass through and become when you go to the electron microscope screen, you find it bright white. If there is a particle which looks dark, because a particle scatters the electrons, therefore it becomes dark in the contrast. So that's how we identify, and we can count the numbers and we can count the area, and this gives an idea about how much amount of swelling has happened. Next one. These are all some of the precipitates on the left side. I also can highlight the material, understand what are all the various matrix and the phase that is formed. This is the chromium carbides. Of course, on the right side is a dark field image. I think this is not part of this discussion. In electron microscopy discussion, I can introduce this at a better way. Next one. So as a function of DPA, now I use a word called DPA, like for money use rupee, for irradiation dose we use DPA, displacement per atom. If it is initially 0, you find all the material is intact with the fold work level with all the defects present. If you go to 20 or 40 DPA slowly, you find round wires are growing, and the wires are the places in which the krypton, all those gases that are during irradiation generated, will go and settle and generate a swelling effect to the structural material. This is what is called wire swelling. Next one. So once you know that it has reached about 40% percentage, you have to stop the reactor, take out the material or the tube. Otherwise, it will give trouble later on. Next one. I mentioned about the coolants. I think water is the best one. If you use a enriched uranium, pressurized water reactor in Kudangalam uses 4% enrichment, and therefore PWR can use water. But we cannot use water because we are not having enrichment plant. We are building up, and currently 5 reactors are using heavy water. That is called heavy water reactor, PHWR, where naturally available uranium U-235, 238 together are present. Canada helped us to establish these reactors. And sodium cooled fast reactors, we have experimental setup FBTR in our center, and PFBR is already almost in the commissioning stage. The important advantage of sodium I have mentioned. The metal melting point is 90 degrees Celsius, boiling point is 900 plus degrees Celsius. Therefore, this is the best coolant available and the cheaper also, and therefore we are using that. Other liquids are possible. Lithium organic liquids can be tried, but experience is very less. Heavy water plant in Tuticorin, Tamil Nadu, and India is #1 in heavy water production. Okay, next one. This is one of the experiments which I have done with the mechanical engineers, where a sodium, if it gets leaked into a steam generator tube because of a small hole, it can generate sodium water reaction, and resultant hydrogen will be checked by hydrogen meter, and therefore one can understand that the reaction has happened immediately, shut down the system. And this is tested for generating the experimental data. For want of time, I would skip the next 3 slides. Next one. Next one. Now, I also mentioned about boron and cadmium. As I have mentioned, in neutron absorption, boron and cadmium are used. Cadmium is good for thermal neutron arresting, whereas boron is for fast neutron arresting. Other than this, do we have anything else? The next one. The next slide shows there are researchers who have told europium oxide is very good. So one can do, so I request the material people who are working in material science or chemistry or physics always can generate more new data through R&D and support the system of our reactors. Next one. Coming to the shielding material, I mentioned aluminum, lead, concrete, and as you know, on the left side, the alpha radiation, which can be stopped by a paper or a hand, beta still easily by a paper, whereas the gamma is the most important thing, and neutron is another dangerous thing. So therefore, gamma, how do we stop? With aluminum, it is alpha only, beta goes a little bit, Whereas if you look at lead and concrete, they are very good for stopping lead for gamma and concrete by neutron. And therefore, all our reactors, as Lanita also mentioned, taken care by two different levels of stoppages so that shielding is comfortable to stop all these things. And lead is extracted from galena ore. I think this is for the children. Next one. Next slide. Events. This is again a depiction how the three different radiations are stopped. And people who have seen X-rays, they use shielding by lead. People who have seen alpha and beta, they can be stopped by hand and aluminum. And neutron has to be stopped by concrete. Next one. Radioactivity and ionization. How do we understand this? They decay. There is a unit. Becquerel is the name of the scientist whose name is used as a unit for radiation, how much it is. 1 becquerel is equal to 1 decay per second. And ionization radiation, it goes as a inverse square law. So very important. Physics aspects very fast and covering it, and scattering, absorption, all these things are in that fashion. You look at on the right side, how do we understand how much radiation is present? There are units like Gray, Sievert, these things are there, and this requires a lot of time. These are all counts per second, and their doses are measured. Next one. And how the decay occurs? The decay is exponentially decreasing, and therefore for each isotope we say what is called half-life. If you look at the useful radioactive carbon-14, which decays and converts into nitrogen, so it is carbon dating is a very important application for understanding the life of age-old material archives. And very important aspect of how do you understand what is half-life. To start, times G is equal to 0, 100 grams you take, after 12.3 years, you find it becomes 50 grams. And after 24.6 years, it becomes 25 grams. This is how a half-life of 12.3 is mentioned for a particular material. So if once you know the half-life, you can understand how much it will be there at the end of a certain number of years. So it clearly shows how it decays. So half-life is very important. Next one. Gamma ray interacts with matter, very important. 3 different methods. This is again physics. Photoelectric effect, as introduced by Einstein. Compton effect, Arthur Compton. And pair production, very important, where electron and proton, positron are generated, and positron is invented by Anderson. And how the gamma ray decays, again exponential. I is the initial is I0, it becomes exponentially minus mu ds. Mu is absorption attenuation coefficient, and if you divide by mass, this mass attenuation coefficient can be there, and which is listed also, found out for various materials or metals. For example, lead is 6 times better than aluminum. For want of time, I'm not covering further details. If you click, there are 3 more slides, schematic of how a photon electric effect, how the Compton effect, and how next one, the positron generation. These things are shown. Okay, these 3 slides are shown. Please refer to some of the things, these things in the physics book, textbook, it will be there. Coming to the almost the last portion, uranium, what happens in the reactor? Uranium is mined, and then it is sent for fuel production, and it is sent inside the reactor. After the reactor has used it, the spent fuel goes to reprocessing, not dumped. When you do a reprocessing, you get a fissionable material that is separated out up and goes up further for production in nuclear fuel complex as oxide fuel, and then it is sent inside the reactor. And if you look at the waste that is generated, all are very, very less. And these are all carefully taken care. The next few slides in a very beautifully brought out. Next one. If you compare, before I go, a nuclear waste generated from a plant and a nuclear weapon, the 3 isotopes, the abundant one is U-238 and 235 is the fissionable one, 0.7, 234 negligible. If you enrich a little bit through enrichment process, 1.5% uranium-235 is only needed for a power reactor. But if you want to make a bomb, 85% uranium-235 is needed. what is the damage that is happening to a person. If one person needs for their entire life to be satisfied with nuclear energy, the waste generated will be only of the order of a small can. Please press next slide. You can see the can. This is the waste that is being generated. So therefore, we are not generating waste. We are not generating waste, huge amount of waste, like what is being produced by thermal plants, or for example, the coal-based fossil power-based plants. Next one. Next slide shows once through nuclear fuel cycle. This we are not using. That is whatever we mine, we enrich and take it into a fuel fabrication, put it inside the reactor, and then they put it in after the reactor irradiation is over, put it inside a short-term storage and dump in zeolite for long time. This is not followed by us. Next one shows a very important thing that's called closed fuel cycle. This is what India is practicing. After the ore is being mined, the ore is getting converted into uranium oxide. Enrichment, if it is done, then it is going to fuel fabrication into the reactor. And after this, when you reprocess the whole material, you can use extract of very good health and medicine, cobalt-6, CH, very good isotopes, industrial use certain isotopes, food and agriculture. This itself can form a beautiful lecture by one of our colleagues. And uranium after the irradiation can also be further used, because plutonium 239, uranium 238 can be put again, and if it is the rest of the things after use will be only dumped as a waste. Next one, how do we go for the waste? I also animated the Uranium Corporation of India, UCIL, where the uranium is mined there. For round of time, again I am skipping these details. Next one, how do we dump our waste? We are using glasses. The glass has got advantages, therefore we are using glasses. However, there are various synthetic rocks, calcine, many other things are there. You can do a very good, excellent research on this. And synthetic rock, zinc rock, is also being done by our people in chemistry. Beautiful research is going on. So we are exploring, as I mentioned, the amount of waste generated is very less. So to dump them, we can generate easily, dump them inside the glass. Glass is very stable. Next one. And safety wise, I think Dr. Anita also mentioned, after Fukushima, on the right side, the dark thing, you can see that the Kudangalam reactor has been given excellent double containment, passive heat removal, everything to take care of any calamity. On the left side, you can see our fast breeder reactor is provided with what is called the core catcher arrangement. In case of a melting, the core is taken care by 1,000 tons or sodium, which will cool it nicely so that there won't be any serious bomb-like explosive reactions. So it's a very useful arrangements. Mechanical engineers, along with all the reactor physicists, everybody does a very unified work so that safety can be incorporated in our reactors. Next one. The reactor building also, if you look at compared to Fukushima, we have taken care of the level above the sea level, such a way that this will be able to stop any calamity easily. You understand where the battery is located, 12.3 switch gear, safety, all these. And these are all given in many of the things, newsletters which are available in our net, www.igcr.gov.in. So you can go through these things in detail. Next one. Next slide. So this, in fact, Asia is having 1/3 of the number of reactors that's going to come in the next few years. Out of the total 67 reactors, 47 are going to be in Asia. Therefore, Asia is going to be a giant in nuclear energy. Next one. And I invite all of you, all young people, to have a career in our Department of Atomic Energy. Though it is very small letters, you find that there are several places where throughout India one can get hold of a place to serve the Department of Atomic Energy. If you look at the east, Kolkata, VECC is there. Physics people can easily go and bridge, all those things are there. Saha Institute of Physics is there. Heavy water board is having several plants. So chemical engineers have excellent opportunities. If you look at on the east side, west side, similarly, we have many places. IRE, as I mentioned, Indian Rare Earths have got excellent places throughout India. So next slide, please. Next slide shows the Atomic Energy Commission, various acronyms. Quite often you will come across BRC, Baba Atomic Research Center, IGCAR, Indira Gandhi Center for Atomic Research. These are all the places where research is being done, R&D. AMD is Atomic Minerals Division, Hyderabad. BECC, Kolkata, Variable Energy Cyclotron Center. Power sector, where power is generated, Nuclear Power Corporation, IREL, and Iranian corporations, ECAL, Electronics Corporation of India Limited. Bhavani is Bharatiya Navigaya Nigam. Heavy water plant, industrial units, NFC, nuclear fuel complex, BRIT, and all these things are there, and supporting units are there. So you are welcome to join us. Next one is a red carpet welcome to all of you. All youngsters, you are welcome to Department of Atomic Energy. And the next one, next slide, shows 4 different very important references. Okay, one by the number 2 is by our own senior colleague who was formerly of our BRC, excellent book. And next one, you have always the best one is the Google. And the last one, before you go into the quiz. The quiz consists of 5 questions taken one at a time for the audience. You don't require not more than 10 seconds to answer. All the questions, 5 questions, are from the same PowerPoint, and I have here and there highlighted the questions. Shall we go for the quiz?
Thank you for your scintillating talk on selection of nuclear materials and choose of the cooling materials, which will be very useful for the students, research scholars, and teachers, sir. So now I request you to conduct the quiz, the short brain piece, sir. Please, so in this regard, I request the participants are requested to post their answers in the chat box, and also the participants who are watching in a YouTube stream can post their answers in the comment box. Sir, you please, okay, you can start the question, sir.
Karthik can move slide carefully, one slide. Yeah. The important elements for nuclear industry are mined by a government limited company which has several plants located throughout the India. It is commonly referred as IRE. What expand this acronym? What is IRE? Yeah, you can put it in the chat box. Yeah, we can shoot the answer. 10 seconds are over. Yeah, it is Indian Rare Earths Limited, IREL. Okay, good. We'll go to the next one. The second slide. Thanks for the people who answered. Best wishes. I show on the right side a person. I have not shown this picture, but however I mentioned about him. Beryllium, californium, curium, mendelium, plutonium are all invented by the support of a famous nuclear scientist and his colleagues. In recognition his student, Albert Guerrero et al., they invented another element and named it after this scientist. Please answer, please identify this great scientist, nuclear scientist. I talked about him.
Now the participants are posting the answers, sir, the chat box.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Yeah, it should answer. I think somebody got it correctly. It is nobody else other than seaborgium. The element is seaborgium. Glenn Seaborg, in recognition of his legacy, the element is called seaborgium. Element number 106. Next one, please. The gamma radiation can be shielded using this metal. Identify this metal. Yeah, I think this is quite easy to answer.
Most of the participants are giving the answers.
Excellent, 100% answer. Yeah, should answer, please. Thank you. Next one. You have to identify what this nuclear scientist is looking at in a bakery. Slightly cryptic. I spoke about this. Not sodium, not oven. I think somebody got it correctly. Yes. Shall you should answer? Yeah.
A few minutes, sir, the participants are posting their answers.
Yeah.
The chat box.
5, 4, 3, 2, 1. Yes, it is cake. And as Subbalashmi and other people have clearly got, it is yellow cake. I also showed it in my slide. Yellow cake is nothing but uranyl oxide. Next one. I did not talk about this, but the people who work in the radiation, they wear this badge. Unfortunately, I did not talk about this. You have to expand this acronym. Not top level. I got, somebody has got it. Okay. 2 people have got. Yeah, I think we can shoot answer.
Yes, sir. Yes, sir.
Thermoluminescent detector. Okay, dosimeter detector. So how it radiation interacts with the luminescent material, and therefore changes that is happening can be read out in terms of the amount of dose received. Next one, I think it's over. Yeah. So I should thank all of you.
Thank you for sir, thank you for your wonderful talk about selection of nuclear materials, as well as you have asked wonderful questions. Most of the participants have given the correct answer. Now I request the participants to raise their hands for live interaction in the Zoom. We have some questions in the YouTube also, sir. First, okay, we'll clarify the doubts of the participants from the Zoom.
First, dear participants, can you unmute yourself, or if you have any queries, raise your hand. The first, Narasimha Gola, unmute yourself and ask.
Narasimha Gola, okay, please unmute yourself. Okay, we are given the permission to you. Narasimha Gola, please unmute yourself. Narasimha Gola.
Okay, sir. Can you go to YouTube, sir?
Yes, sir. Sir, we have a few questions from the YouTube participants. The first question is from the Ibrahim. So, can we use protactinium as a nuclear fuel? Can we use protactinium as a nuclear fuel? This question is asked by Ibrahim in the YouTube stream. Protactinium.
Yeah, it's all availability. See, if you look at the fuel in the slide I have shown, the availability of the material, and if you look at the first important diagram is atomic number versus the binding energy. And it should be high atomic number material. So if this goes into that domain, you can use. If you look at after iron, there are many elements are there. But why we use uranium? Because the atomic energy, atomic number is high. It's also abundant and available to a certain extent. If it is available in the form of only grams, it is of no use. You can only do some demonstration. So well over uranium and plutonium and thorium based, when it is converted into U-233, this is being engaged as the fuel.
Thank you, sir. And one more question from Mr. Praveen in the YouTube. How can we rectify void issues?
Void?
Yes, void issues.
The cold work, 20% cold work, which we give to all our structural, the stainless steel tubes, prevent this void swelling at least for 2 years, and therefore they are able to survive. Secondly, these stainless steel are added with additional elements like silicon, phosphorus to a certain extent, and now titanium also. These three things help us to stop the void formation. How? It is these atoms can stop the vacancies from agglomeration. Therefore, titanium added stainless steel, 316 stainless steel, the grade, is we used engage in our hospital reactors, and we are additionally silicon phosphorus added IFAC steel, which is also being proposed as the next generation reactor with grade material. So we can control the void swelling by using these advanced materials. The research is going on, and we also established these two materials.
Okay, sir. So I have one question. You have talked about the choose of coolant materials. What are the factors that can affect the coolant property of this material, sir?
I think I have listed this. The most important thing is a coolant should take away the heat. So specific heat capacity is very important. The more it is able to extract the heat comfortably. Otherwise, it itself will become problem, and it should not become volatile. That is, water should remain as water. Water should not become vapor. For example, that is why we are trying to contain it by pressurizing it. That's why pressurized water reactor, pressurized heavy water reactor. Whereas in sodium, we are not doing that, because sodium is able to remain liquid, take away maximum heat, and it goes into exchange of that heat with water, another water. So there is a secondary circuit, and then that takes away the heat and convert itself, water will convert itself into steam. So therefore, the most important property is, in the sodium case, low melting point, very high boiling point. That difference is 90 to 900 degrees Celsius. In the case of water, it is not so. Therefore, water will boil. To avoid it, they are increasing the pressure and keep it liquid. Okay? So this is the most important thing. Specific capacity, most important. No corrosion. For example, sodium is very good. And if you see the pumping capacity, sodium will have a little bit of difficulty compared to water, but better. But lead is a heavy element. It will not be easily pumpable. But still, people are thinking of R&D and this lead also. But corrosion wise, sodium, if at all it interacts to some small lake, gets converted into sodium hydroxide, oxide and hydroxide subsequently, this will attack the structural material, particularly when it is shut down. I think I have answered.
Okay, sir. And one more participant raised her hand. Queen Elizabeth, madam, please unmute yourself. Queen Elizabeth, madam, we are given the permission to you. Please unmute yourself. Queen Elizabeth, madam, please unmute yourself, madam. You have raised your hand. Queen Elizabeth, madam. Okay. Okay. Yes, ma'am. Please. Okay. Please ask a doubt, ma'am. Hello. Queen Elizabeth, madam. Now you can ask, ma'am. Your mic is unmuted. We can't hear you, madam. Okay, so any more? So there are no more questions, sir. Thank you. Okay, so much for your yes. Thank you so much for clarifying the doubts for the participant questions, sir. Now I request Dr. A. Nadraj to give the introduction for Dr. Karthik, sir. Sir, Dr. Nadraj, sir, please.
Yes, sir. Thank you, sir. Very good afternoon to one and all. I have a great honor privilege to introduce Dr. V. Karthik, Head SMCS PIED Igcar, who is going to deliver the talk on mechanical behavior of material, the third session of this virtual workshop. Dr. V. Karthik is currently a senior scientist at the Indira Gandhi Center for Atomic Research, Igcar, Kalpakkam, India. He holds a postgraduate in physics from University of Hyderabad, an engineering degree in metallurgy from the Indian Institute of Metals, and obtained his doctoral from University of Madras, working for the past 25 years in the metallurgy and materials group of Igcar. His research interests include mechanical behavior of materials using conventional and small-sized specimen and nuclear material of fast reactor and analysis of their in reactor performance. Dr. V. Karthik was a recipient of Young Engineer Award in the year of 2006 from Department of Atomic Energy, peer-reviewed journals, international and national conference proceedings, and once book and small specimen testing by CRC Press. Well, on behalf of the department, I welcome you, Dr. P. Karthik, sir. I hand over the session to the Karthik. Karthik, sir.
Karthik, sir.
Yes,
Sir, please share your screen and you can start the presentation, sir.
So, is my screen visible now?
So already the permission.
No, sir, no, sir. Sir, you please stop share the permission PPT, sir. Then you can open the.
Shall I say I have already stopped it? Shall I say new share or resume share?
No. You just click the stop share. Then you click the new share, sir. New share.
Okay. Is it now?
Yeah.
Yes.
Now
okay.
It is clear, sir.
Yeah. So thank you, Dr. Nadraj Ayamperumal, for a brief introduction. A very good evening to all of you here who are present on the online media. Am I audible?
Yes, sir. Yes, sir.
Okay.
Okay.
So first of all, I place my thanks to the SRM Institute of Research and Technology for arranging this program, and also my job has been done quite simple by the two previous speakers, Dr. Parameshwaran and Dr. Anita, who had given all the required introduction for this lecture. So the title of my presentation is Mechanical Behavior of Nuclear Materials. Yeah, this talk will cover the basics of mechanical behavior of materials and the requirements for testing. I will also dwell on the materials in the nuclear reactor and the conditions. Briefly on the effects of radiation on materials and the consequences. And I will also have a few videos and finally few questions. The mechanical behavior means how the material responds to external mechanical loads. Common loads are tension, compression, shear, torsion or twist, and bending. In tension and compression, the loads are acting perpendicular to the surface. They are considered, while in shear, the loads involve that acting along the surface. So these are the five basic loads experienced by the material. So we come across these simple loads and stresses in our everyday life. For example, in a tug of war, you have a tensile load, or on a rock you can see due to a larger object placed over it. And for example, in a suspension bridge, the weight of the deck is supported by the vertical steel wires, and the weight is transferred by the cables to the towers, which in turn transfer the weight to the ground. So the cables are under tension. You can see these red colored cables are in tension, while the tower supports are in compression. So these loads of tensions and compression we come across this in everyday life. And in most of the cases, these stresses are combined. For example, in a simple bending, the object bending downward experiences a tensile stress or a stretching in the upper section and a compressive stress in the lower section. Similarly, an object or a tank with a gas or a liquid under high pressure inside, the tank experiences circumferential stresses called hoop stress, as well as longitudinal stresses along its length. So these are stresses in 2 or more directions. Similarly, rotating components often experience torsional stresses. You can think of a Rubik's square, which as a rotating part against a stationary part, which is being twisted or subjected to torsional forces. Similarly, the rotating parts in a turbine or a generator will be subjected to torsional loads. The shear stresses are those acting along the surface of the undergoing deformation, and the shear stresses are quite common in riveted joints. You can see the shear stresses acting along the surface, around a riveted joint. The mechanical behavior of materials are described in terms of mechanical properties. The important mechanical properties are stiffness, strength, ductility, toughness, and hardness. Stiffness refers to the resistance of a material to elastic deflection. That is, it is defined, or it is in terms of the elastic modulus or Young's modulus. The strength is the stress required to fail a material, the strength required to fail on a particular load configuration. The ductility of the material refers to the ability of the material to deform without failure. So its ability to deform so that the failure is taking after quite considerable deformation. The toughness is the ability of a material to withstand the loads in the presence of a flaw or crack. So it is a property which combines both strength and ductility. And the hardness is normally referred to the resistance to a penetration or indentation by a specific tool. So the hardness is more or less related to the strength, the yield strength or the ultimate tensile strength, while the ductility refers to the ability of the material to undergo a lot of strains before it fails. So why do we need these mechanical properties? We need them for the design of engineering structures, be it buildings, for transport structures, industrial plants, power plants, and many more such applications. So we need these parameters or mechanical properties for designing the engineering structures. They are also required for manufacturing the product during the material processing and fabrication. Even the smallest item we use in our daily life, like safety pin, jump clip, springs, staplers, pens, to large components like turbine, boilers, reactor components, fossil power, steam generators, many such components are processed from the ore to a final shape, final form. So during the processing, the knowledge of mechanical property is required for ensuring that the final component is as per the specifications. So it is also required to know and make informed choice of using the materials, the right materials for the right applications. So the mechanical behavior of any material is studied by applying an external stimulus like force, pressure, or displacement in combination with heat and in some cases with the environment and measuring the response of the system. The load could be simple tensile, compressive, shear, or a combination of these. The magnitude could be a constant load, or it could be a monotonically increasing load, or it could be a fluctuating load. And the duration of load could be a fraction of second, or it could be few hours, or the duration of the load application could be for many years. I will give some examples. So the load, the magnitude, and the duration has a wide range of values and applications. The mechanical tests are performed on specimens made from the material, and the tests are conducted as per some recognized standard. So there are broadly three classes of tests. The simple tensile test involves just a constant pulling of the sample, pulling of the material, or a constant stretching of the sample. And the strain rate, the strain is normally defined as the change in dimensions divided by the original dimension, or is a ratio of change in dimension to the original dimension. It is a unitless quantity, and the strains due to the applied stress are normally strain rate is in the range of 10 power minus 2. So the tensile test normally takes a few minutes, or could be a half an hour duration to pull it to failure. The other class of test is called the impact test, which is a very fast impact blow of the material or the sample. The duration of the test is just a fraction of a second. I will show you some pictures. And the strain is taking place in a very short duration of the test during the impact blow. So the strain is changing at a very fast rate. So you have a very high strain rate. The strain rates are typically of the order of 10 to the power of 2 per second. On the other end of the spectrum, we have what is called a creep test, where a constant load is applied at mostly elevated temperatures and the material strains at a very slow rate. There is a straining of the material at high temperatures, but it strains at a very, very slow rate. And this test takes months to years. And the results of this test are used for the design of high temperature components, especially in nuclear reactors and other fossil powered and other fossil fired power plants. A typical tensile test curve is described in this slide. A sample consists of a uniform section of the material, which is machined from the available material, and with a slightly expanded portion for gripping the sample. The sample is gripped in a universal testing machine, and you have an extensometer to measure the extension of the sample. You also have a load cell to measure the load during the pulling of the sample, and the crosshead moves at a constant speed or a constant displacement rate. So during this pulling, you can see the video here. During this pulling, you can see that there is a small extension of the sample, and as long as this is elastic, within the elastic limit, as long as this is within elastic limit, if you suspend the test, or if you stop the test, if you unload the sample, it will trace the path. It will trace the original path. The material is said to be elastic, and the slope of this curve is the elastic modulus. Beyond the elastic limit, the material strains goes into the plastic deformation. The plastic deformation or permanent deformation refers to the plastic strain which accumulates in the material. Which accumulates in the material, and and the stress strain curve slowly bends to a point where the material hardens. You can see the material hardens here. The material hardens, and as it comes parallel to the strain axis, there is a thinning in the sample. There is a localized deformation in the sample, which leads to a formation of a neck and final failure. So this is a typical stress strain curve obtained from a tensile test. The yield strength is normally is a point which separates the elastic deflection and the plastic deformation, and the yield strength is determined as normally using a procedure called 0.2 offset, where if you stop the test at the yield stress, at the 0.2 yield stress, and unload the sample, you will have a small permanent deformation equal to 0.02% strain. So these are the typical images of the sample, and as you can see, the sample starts to yield beyond this, undergoes increase in length and reduction in the diameter, and beyond the maximum load corresponding to the ultimate tensile strength, you have a localized thinning of the sample leading to formation of neck and final separation. So the yield strength is the value of the stress at a specified offset at this location where there is a permanent deformation. The ultimate tensile strength is the highest value of the stress on the stress strain curve, and the most important parameter is the ductility, which is defined in terms of the percentage elongation, which is the change in the length of the sample divided by the original gauge length. So this is a most important parameter which defines the material as being ductile or brittle. Similar to tension, one can also carry out compression test when the sample is subjected to compressive load between two compressive platens in a test machine. It is normally carried out by compressing cylindrical samples between two well lubricated dies, and the sample begins to bulge, known as barreling. For most of the materials, the properties in tension and compression are the same. But however, for materials which cannot be tested in tension, like concrete, ceramics, and composites, which are very brittle in nature, once you start pulling in tension, they will fail quickly in tensile mode. The compression test mode is very useful for materials which are quite brittle in tensile mode. So I have briefly introduced two words called brittleness and ductility. The brittleness is a measure of the material's inability to deform before failure. You have a linear elastic portion, but beyond the plastic, like beyond the yield stress, it is not able to deform, so it fails at a very short strain, very small strain, and so it's said to be a very brittle failure. So I'm sorry, example of a brittle material is glass or high carbon steel and ceramics, while the opposite of brittleness is the ductility, where you can see significant deformation of the material in the plastic regime. In the after the yield strength, there is a significant deformation of the material before it fails, and this strain is the measure of the ductility. So examples are low carbon steel, aluminum, and copper. So when the material fails after deformation, the surface of the sample which has failed can also indicate whether it is a ductile fracture or a brittle fracture. A ductile fracture is normally accompanied by significant plastic deformation. So when there is a plastic deformation, there is significant shear lips formed with a so this this, while in case of a brittle fracture, there is little or no plastic deformation. So it is almost a flat fracture. So in the ductile case, you will have very large elongations or very large strains, before failure, and you will have a kind of a cup and cone fracture. While in a brittle fracture, it will be little or no plastic deformation. It will fail immediately after the elastic limit, and the failure could be quite catastrophic. So in the engineering applications, ductile fracture is usually more desirable than brittle fracture, because ductile fracture always occurs with sufficient warning, or because you have the plastic deformation, you have a crack initiation and a crack propagation. So you have sufficient time or warning to know that a ductile fracture is going to take place. Whereas in brittle fracture, there will be no plastic deformation. So there will be no crack initiation, or there will be no crack propagation. There will be a crack initiation and it will fail instantaneously without any warning. So examples of such things are, this is an example of a pipe failure. This is normally called guillotine failure, where you have the tube has significantly deformed, so it has good ductility. It has though failed, but it has retained its it has not failed, though it has undergone large deformation. It has still retained its identity. Whereas in a brittle failure, you will normally have very small plastic deformations, and you will have lot of multiple. So you have lot of pieces which has failed after the failure. So brittle failure normally is accompanied by a failure into multiple pieces. Now coming to the next test, the impact test, which is carried out under dynamic loading. As we know, most of the ships during the Second World War were failing in a brittle fashion without no warning or no propagation, with no crack propagation. Normally a material fails with initiation of a crack and the propagation leading to final failure. But in brittle fracture, there were lot of failures taking place in the early 40s, 1940s, and it was found out that steels with internal cracks or defects breaks easily under a combination of low temperature, for example -20 degrees to -40 degrees or below, and impact blow. So steels which have a crack, which are subjected to low temperatures and which are subjected to impact loads, fail in a very brittle fashion. They don't absorb any energy, they don't undergo any ductile deformation. So from this experience, the impact test was born out of these failures to quantify the fracture of the material, or to understand the fracture of materials under a high strain rate, the impact blow, and under a triaxial stress. The triaxial stress, because a crack introduces either a biaxial or triaxial stress in a material, and all materials contain flaws. So the flaws introduce, though the applied loads would be uniaxial tensile in one axis, the cracks or the notches in the sample could introduce additional stresses, and so this stress involves an impact blow using a pendulum striker, which has a striker of this shape. The specimen is a notched specimen. A small notch is there on one half. A typical size of the specimen is 55 mm in length and 10 mm by 10 mm in cross section. And this sample, after it's placed here, it is impact blown, and the rise in the pendulum is used to measure what is the energy absorbed during the fracture. And this energy absorbed during the fracture is called Charpy impact energy. So all the steels, most of the steels which have BCC structure, body centered cubic structure, were found to have a ductile failure. They had sufficiently high energies were involved when the test was done above room temperature and at ambient temperatures. But when we go to sub-zero temperatures, we found that under this impact loading, a notched specimen requires very small energy to fail, which failed in a very brittle fashion. So I would like to show you this. There's a notch specimen which is placed. The pendulum is released, and you can see that the pendulum, the energy obtained in the failure. So these are the features of the brittle failure here. Similarly, the impact energy is also a function of temperature, as I indicated you. So the materials with BCC structure show very low energies when tested at sub-zero temperatures. However, when the temperatures are beyond 0 degrees and into the ambient and at elevated temperatures, they show a ductile behavior. Whereas materials like FCC with FCC structure like stainless steels do not show this ductile brittle transition behavior. So all the materials, steels, especially carbon steels and high alloy and the alloy steels which have a BCC structure exhibit this ductile brittle transition, and this transition temperature here is normally taken as the midpoint of the upper and lower shelf energies. So as you can see, as long as these temperatures are not in our operating conditions, the material can be safely used. But however, if the ductile brittle transition temperature is towards the operating temperatures, then the material is not safe for use depending on the operating temperatures. So now coming to the other spectrum of testing, the material strength is also a function of temperatures. As we go to elevated temperatures, more than 40% of the melting point, when we go beyond the 40% of the melting point of a particular material, then the material starts to what is called creep. Creep is nothing but a permanent strain in the material, a permanent or plastic strain in the material when it is subjected to a constant load at a high temperature which is greater than 40% of the melting point. For example, if steel has a melting point of 1460 degrees Celsius, then beyond these temperatures, beyond 550 or 600 degrees Celsius, the steels undergo what is called creep deformation, or steels have to have sufficient creep strength for use at elevated temperatures. And these strains take place for loads much less than the yield load. At room temperature, we saw that the material up to yield load does not undergo any plastic deformation. It is only elastic. But however, at elevated temperatures, above 40% or 50% of melting point, even if the loads are less than the yield stress of the material in the presence of temperature and the lower loads can undergo permanent deformation or plastic strain called creep strains because of the effects of high temperature on the microstructure of the materials. So creep strength is very important for high temperature applications, especially for turbine blades, steam generators, thermal power plants, nuclear power plants, where the operating temperatures are close to 50% of the melting point of the particular material. Now coming to the nuclear reactors, as we know, we had a very good introduction and on the basics of the nuclear reactors, the various types of reactors which has been in use. And as you know, in a nuclear reactor, controlled chain reaction takes place that produce heat through a physical process called fission, and that heat is used to make steam and that spins the turbine to produce electricity. The reactors use uranium and plutonium for nuclear fuel. The uranium is made into small pellets and they are stacked together inside the core into metal rods or metal tubes called fuel rods. The uranium pellet is stacked inside a metal tube and as fuel rods, and typically a reactor core shown here, has more than 200 such fuel rods, and they are bundled together to form a fuel assembly. And the reactor core consists of few hundred of such assemblies depending on the power. And inside the reactor, the fuel rods are immersed in water or heavy water, as the case may be, or it could be sodium coolant. And the moderate and in the pressurized water reactors or in the thermal nuclear reactors, you have the moderator as well. So these so the core materials consist of the uranium oxide, which is enclosed in an alloy of zirconium in case of thermal reactors, or stainless steel in the case of fast reactors. These are the various materials used. They have been already covered, but I will just go into these two important materials. And the fuel rod cluster is assembled into fuel assemblies, which will be the basic handling unit. And you also have the pressure boundary. In the case of a pressurized water reactor, you have, or in the case of a pressurized heavy water reactor, you have the coolant which is at a elevated pressure, high pressure, so that it remains in the liquid state. So the boundary of the pressure is the pressure vessels. This is the cylindrical volume here, the pressure vessel, which is made up of steel. So there is a pressure boundary, and then you have containments, which is concrete and steel structure. So we have 5 barriers from the fuel to the outer environment, namely the fuel rods, then the fuel assemblies, the pressure tube, and then the containment. So there are 5 barriers from the fuel to the external environment. This is one of the very important safety features. As you know, inside the reactor core, the materials are subjected to very hostile environment, very challenging environment, because you have a temperatures of around 300 degrees Celsius in a pressurized water reactor. You have temperatures of around 500 degrees in a fast reactor. So it is a very high temperature furnace. You have coolant, you have either water in pressurized water reactor or sodium, and the coolant is also at a very high pressure in case of pressurized water reactors. In fast reactors, it is at a nominal pressure. More importantly, you have the neutron environment. The neutrons with sufficient energy greater than 100 keV can disrupt the atomic arrangement or crystalline structures of materials. So the material in a reactor core are subjected to a combination of high temperature, neutron damage, and the coolant pressure. So as indicated by the previous speakers, the neutron, on interacting with the atomic structure of the material, can cause sufficient disruption in the atomic arrangement of the crystalline structure. While the gamma rays, beta rays, and alpha particles interact only with the electrons surrounding the nuclei, they have no effect of, there is no effect of the ionizing radiations. The gamma rays, beta and alpha are ionizing radiations. They have no effect on metallic structures. But however, neutron, being a neutral particle, can penetrate deep into the metallic structures, and it interacts with the nucleus of the material, and it can cause significant disruption in the atomic arrangement of the materials. So neutron induces various defects in the material, which includes vacancies, interstitials, voids, which are combination of vacancies and other defects. So the vacancies, which are combined to form voids, they cause the steels to swell. So this is a most important damage mechanism happening in the material, which is used in the core of the reactor. So what is the effect of this neutron damage? The fuel rods made of stainless steel undergo change in dimensions, and they undergo distortions because of these microscopic voids. The microscopic voids cause a macroscopic increase in dimensions. This is the fuel rod before it is put into the reactor, and after it is put into the reactor and run for few years, you can see there is an increase in the length as well as the diameter of the fuel pin. So this is the initial state of the fuel pins inside the cluster, and you can see the bundles, the fuel pins start to swell, and you can see a lot of distortions in this. So you can see a wavy pattern which is taking in the fuel pins. So what happens is, initially you have space for the coolant to flow between the fuel pins. But due to increase in dimensions, the fuel pins are left with little space between them for the coolant to flow. If the coolant flow is restricted, there is obviously an increase in the temperature because the heat is not extracted. The heat produced inside the fuel rod is not extracted by the coolant if there is no coolant flow, and this could lead to overheating, or it could lead to loss of the mechanical strength. So on reaching certain unacceptable dimensional changes, fuel rods have to be withdrawn from the reactor. The fuel rods cannot be in the reactor because the coolant flow is not taking place, or there is a effect on the thermal hydraulics, so they have to be withdrawn. So swelling and dimensional changes affects the residence time of the fuel rods in the reactor because of the changes which happens because of the swelling. Similarly, the effects of the neutron damage. The neutron produces so much defects which causes the material to harden. So when you do a tensile test, the neutron irradiation causes an increase in the stress. An unirradiated material will show sufficient plastic strain after elastic deflection. However, after irradiation, when you test the material, you will see that the strength is increased, but the ductility is reduced. So the material undergoes what is called hardening because of the defects. The defects act as barriers for the material's flow. The material cannot flow easily because the defects act as barriers. Lot of defects are produced. These barriers increase the strength of the material, but at the same time, they reduce the ability of the material to undergo plastic deformation. So there's a loss in ductility, making it more brittle. So fuel rods could fail in the reactor in a brittle fashion. I explained that a brittle fashion involves no plastic deformation without any warning. So fuel rods could fail without any plastic deformation. You can see such few examples of a fuel duct failure in a fast reactor which has failed inside the reactor. So once the failure takes place, the fuel cannot be used inside the reactor. It has to be carefully taken out for other processes, and it leads to lot of shutdown and outages. So the effect of neutron damage on the stress strain material can affect the mechanical stability of the fuel rods and the fuel assemblies. So while the strength increase is acceptable because the material hardens, you have sufficient strength or sufficient hardness, but the ductility reduces, which is not acceptable. The ductility reduces here. You can see it reduces with increasing neutron damage. So that is what is unacceptable. So we have seen that apart from these effects, there are these pressure vessels which are permanent components. These pressure vessels are permanent components in the reactor. They also receive this neutron dose. They are also subjected to neutron bombardment, and due to neutron bombardment and the defects produced in the material, this is a pressure tube. It's a very big component compared to the size of a normal person here. It is the pressure bounding barrier, and which is enclosing the core. And most important is these pressure vessels are normally made of high alloy carbon steels. These neutron irradiation also affects the properties of the pressure vessel steel. What it does is, if we take a neutron irradiated component and make a sample from this component and do an impact test, what we find is the neutron temperature shifts the temperature for brittle failure. Before irradiation, this is the curve. We have to do at least 15 to 16 tests to generate this curve at different temperatures. We do the test to determine where is the ductile to brittle transition. It is the brittle region, this is the ductile region, and this is the transition. As you can see here, in the unirradiated condition, before it goes into the reactor, the transition for the ductile to brittle is much sub-zero temperatures, is much below 0 degrees Celsius. So as long as our reactor temperatures do not come in close to this temperature, there is no major issue. But neutron irradiation shifts this curve. This curve is getting shifted here, the red curve here, after irradiation by certain temperatures, and it is close to the operating temperatures. Once it is close to operating temperatures, these steels are more susceptible for brittle failure. So there is a reduction in the toughness. A small flaw in the material or a small crack in the material combined with an impact load and the neutron irradiation can lead to a large reduction in toughness and failure of this component, which is a very, very severe incident. So this pressure vessel steels have to be such that they have negligible or very small increase in the ductile brittle transition temperature. So far, we have seen that the components in the nuclear reactor exposed to high temperatures and neutron fluence undergo increase in dimensions, they undergo distortions, they lose their ductility and toughness. So, but why are these important? Because these are important because our aim is to maximize the power output from a given reactor, which means the fuel has to be burnt completely. The juice has to be extracted from the fuel completely before it can go for reprocessing. But however, the neutron damage in the material always limits the life of the fuel rod and the permanent components. They 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 result in the change in mechanical properties which will require their replacement before the fuel is burnt fully to extract the maximum energy. So when there is a frequent replacement of materials, it will affect the economics of the reactors. So it is very, very important to improve the materials to enhance its life in the reactor. So there are a lot of improvements by going from in order to reduce the swelling on the material, as Dr. Parameshwaran indicated, we are going for improved materials by changing the chemical composition of the materials, and also for going to other materials like chrome moly steels, 9 chrome 1 moly steel, which is a ferritic steel, which is also known to swell very less. So this low swelling alloy is a separate area of research at IGCAR, and it involves a lot of steps from development of alloy to fabrication of component to also doing a test irradiation in a test reactor like FBTR before it can go into the commercial reactor. So it is a very long chain of research activity which has been successfully carried out. So how and where are these reactor fuel rods examined and tested? These fuel rods are examined and tested because they are highly radioactive, a component which goes into the reactor under neutron irradiation, neutron bombardment. The component which goes into the reactor becomes highly radioactive, and you will have alpha, beta, gamma radiations from the component. So the component has to be handled in a shielded enclosure, and these are shielded enclosures called hot cells, where the component is transferred from the reactor and it is handled inside the reactor. The operator is standing outside this shielded environment. This is a combination of concrete and high density concrete and lead walls, and all the operations and examinations have to be carried out through robotic arms and remote handling. So since the component is highly radioactive, the operator has to be outside the shielded enclosure to handle these components and carry out sample, find out the properties, do sampling, do measurements, and give feedback to the designers and the operators. So I'll just show you a small video of how the experiments are carried out on irradiated master slave manipulator. It has a slave arm which will be, and it has a master arm. The slave arm is actuated and you can do all your operations inside the enclosure. You can see the slave arm inside, and this is a very, very challenging operation here. A normal operation or a test which takes about half a day outside would take more than 2 days inside, because all the operations have to be carried out remotely using this manipulator. So this is a tensile tested sample which is being handled after the test. So there's a chain of hot cells in our facility where the radioactive material is taken from the reactor and tested. So with this, I conclude my talk and I thank the organizers and IIM Kalpakkam for giving me an opportunity. Thank you.
Thank you,
sir.
Okay.
Yeah.
Thank you. This is a very useful talk and informative one. You have explained clearly about the mechanical behavior, mechanical properties of material which is used in the nuclear reactor. So it was well received by us. Thank you so much, sir, for scintillating talk and knowledge shared by us to us in this occasion, sir. Thank you. Thank you so much, sir.
Thank you. Thank you for your nice comments. I have shared my screen here for the questions. Is it visible?
Yeah, visible, sir.
Okay. So I have 3 questions.
Participants, you can answer it in a single chat box.
Yes, I request the participants to post your answers for the questions.
The first question is, which is more ductile in these 2 cases? Which is more ductile? Sorry, which is more? And which is more damaging to materials? Alpha particles, neutrons, beta particles, or gamma rays? And what do you refer to the phenomenon of a slow straining of material under a steady tensile stress called?
The participants are posting their answers in the chat box.
Okay, that's good. Please let me know when I can go to the answers.
Yes, sir. Please give the 2 minutes, sir. Now
Yes,
participants
sure.
are posting the answers. Most of the participants, okay, are the posting the answers. Here. Namta Chhabra, Aniket Podar, Queen Elizabeth, Shivaling, Geeta, Mautazin, Olivia, Ramesh, Irene. They are posting their. They have posted their answers, sir.
Oh, good, nice.
Bhubesh, Sindhu, Narasimha Gola, then Suresh Kumar. They are posting the answer. I request all the participants to post the answers as soon as possible.
In YouTube also the participants are answering.
Okay, sir. Karthik, sir. Okay, you please show the answers.
Yeah, so the answers are. B is the ductile failure, because ductile failure always have some slanting, or it has undergone significant plastic deformation, which means you will have a lot of shear edge, shear deformation. While brittle fracture always will be flat. There's no plastic deformation. So always plastic deformation is under a shear stress. And the shear stress signatures are slanting angles of, these are typical cup and cone fractures. Similarly, for 2, the answer is B, because neutrons are chargeless and they penetrate and cause displacement damage in the material, while alpha, beta, gamma, or ionizing radiations, they interact with the neutrons and lose their energy within a short distance. So they are not as powerful as neutrons in causing damage to the materials. And the phenomenon of slow growth of strain under a steady tensile stress is called creep. Creep phenomenon is very important for designing high temperature or elevated temperature components, where the component or the material is being used at 40 to 50% of its melting point. At those temperatures, the creep mechanisms, the creep properties have to be determined and properly employed for the use of the component. So that's it from me. I am open to
Thank you,
questions.
sir.
Yeah.
Thank you,
Now I
sir.
request the participants to raise your hands for the questions.
Sir, the participants from Zoom, the Prasanna Devi, we unmuted. Please unmute yourself. We ask the question. Prasanna Devi, unmute yourself and ask your question. Next we move to the Radhika Pomalam.
Sir, good evening, sir. It
Yeah,
was
good
a
evening.
wonderful talk.
Oh, thank you so
Actually,
much.
I love this part of physics, and in 11th standard, they have such excellent chapter on properties of materials.
Yes, yes.
So, one question I wanted to ask is, you were saying about neutrons are charges and they cause displacement. Such materials, do they undergo a neutron capture? Will they capture these neutrons?
Yeah, you.
How can we minimize the effect of neutrons on them?
Actually, this when I refer to neutron interaction, it is mostly with the steels. The steels don't have a they don't have a capture property, but you have you have other mechanisms like scattering taking place, elastic
Okay.
and inelastic scattering taking place. So there are multiple phenomena happening. You have neutron scattering taking place. At the same time, the neutrons will also interact with the nuclei, and they also will cause at a microscopic scale. They cause these defects. So these phenomena are happening at different scales. The what I am talking about is at the microscopic scale. The so these phenomena are taking place. In fact.
Sir, what about they are thermal neutrons, isn't it, sir?
No, these are I'm sorry, these are fast neutrons. Mostly the damage comes from energies greater than 0.1 MeV.
Okay,
Because
okay, sir.
those neutrons only have sufficient energy to knock off the atoms from its positions.
Okay, sir.
So
Okay.
the thermal neutrons will normally not have much of energies to knock off. So the energy is above 100 keV roughly, or 0.1 MeV.
Okay, okay. Thank you so much, sir.
Okay,
thank you for the talk.
Welcome.
Mr. Suresh Kumar, please. Yes. Suresh Kumar, sir. Okay. Able to hear?
Yes, sir. Thank you.
Please.
Sir Karthik, sir, thank you very much for your wonderful session, sir.
Oh, thank you so much.
My question is, metal joining is one of the important criteria in power plant, no, sir, by nuclear power plant. What are all the basic mechanical properties have to be checked, qualified for the material joining while we are preparing, sir?
See, yeah, this is a very, very interesting question. I have not covered here because of want of time, but see, the welds are, in some cases, the weld joints are more critical parts, especially in a fuel rod. When the welds are located on the top, the tube is welded at the ends with a end cap. And the welds are also subjected to neutron damage and temperatures, and as well as the coolant. So normally the welds are subjected to lot of quality checks. At the same time, the weld metals are supposed to have equal or better than the base metal properties. So the weld metals are tensile tested to ensure that that they have sufficient strength than the base metals. At the same time, there are certain weld zones, like the heat affected zones in the, especially in the chrome moly steels, which are very weak. So especially when you have a 9 chrome 1 moly steel, the heat affected zones are the weakest in the weld region. The heat affected zone, which is at the boundary between the base metal and the weld metal, those are the weakest zones in the material. So they have to be tested. So simultaneously, wherever base metals are tested and qualified, the weld metals are also tested and qualified for tensile, creep, and fatigue, to ensure that weld failures don't take place.
Okay, sir. Thank you very much.
Thank you, sir. Sir, any question from YouTube, sir? Sarana,
Yes, sir.
Yes.
Yes, sir. There are one question in the YouTube participant. Can we? What are the materials, important materials that can be used for this purpose, or application-oriented purpose? Especially, can we use titanium instead of stainless steel?
See, the most important parameter which Dr. Parameswaran also indicated was with respect to the cost of the material, and it also has to see how it responds to neutron damage, what activation products are produced, and more importantly, whether it can be formed into different shapes and forms. So titanium is an hexagonal close pack structure. So we have to see whether the formability of the structure into tubes, into hexagonal shape, into components, and whether it can withstand those temperatures. So these have to be analyzed carefully. And stainless steel is the universal choice. The stainless steel is a universal choice because of its very good creep properties and other loading conditions like fatigue and also with respect to radiation stability. So the titanium per se is also very costly material. So it will have a bearing on the cost of the reactor, because the fuel, the stainless steels, tubes and the structural materials constitute about 40% of the cost of a fast reactor. So it will have a significant bearing on the cost as well, apart from the other compatibilities.
Okay. Thank you, sir. Thank you for your wonderful explanation for the participant questions. Okay. Ma'am, HOD ma'am, shall we propose a vote of thanks? Ma'am, HOD ma'am.
Sir, Parameswaran sir.
Parameswaran, ma'am, sir has left out, ma'am. He messaged
Dr.
that.
Karthik sir, thank you so much, sir.
Yeah, thank you, madam, for
wonderful
a nice
presentation. I could see the feedback from the participants. Thank you so much.
Oh, thank you so much for the nice feedback. And I take this opportunity to invite participants as well as the organizers to our center, and we can have a lot of interactions.
Yeah, definitely, sir. Definitely, sir. Thank you so much for your invitation, sir. Now, I propose a vote of thanks, respected guests, students, teachers from various schools and institutions. A very good evening to all present here. As an organizing secretary of this workshop, I am taking immense pleasure to propose a vote of thanks amidst the gathering. First, I would thank Dr. Parameswaran, Head, Physical Materials Division, Igcar, Kalpakkam, for his presence and gave consent to deliver a scintillating talk on selection of nuclear materials. Next, I would like to thank Dr. V. Karthik, Head, SMCS PIED, Igcar, Kalpakkam, for his presence and gave consent to deliver a wonderful talk on mechanical behavior of nuclear materials. Then our fruitful thanks to Dr. Anita Topu, ma'am, Scientific Officer E, Corrosion Science and Technology Division, Igcar, Kalpakkam, for gave a consent to deliver a talk on environmental effects on performance of nuclear materials. Next, I would like to thank to Dr. V. Subbiya Bharati, sir, Campus Director, SRMIST, for giving approval to conduct this virtual workshop on Indian Nuclear Program in association with IM Kalpakkam chapter Igcar, especially for the high secondary diploma and the school teachers. Next, I would like to thank our Dean ENT and Vice Principal Academic and Vice Principal Admin for the valuable support. Last but not least, I would like to thank all the students and the teachers from the various schools who actively contributed the participation in this program. Finally, I would like to thank to our management for extending support to bring out this workshop a grand success. Thank you one and all. Now I request Dr. Nataraj sir to post a feedback link in the Zoom.
Yeah, I'm posting, sir.
All the participants, okay, to fill the feedback form. It's mandatory for issuing certificate.
Raman, sir.
I also post the feedback link in the YouTube. Yes.
I am also
Yes.
posting, but again, still they are asking.
I request all the participants to complete the feedback form to issue the certificates.
Sir, YouTube போடுங்க sir. Link not available.
Already posted, sir.
நீங்க போஸ்ட் பண்ணதுல லிங்க் இல்ல.
பாருங்க, இப்போ again post பண்ணிருக்கேன் பாருங்க. Now again posted. So if it is possible, okay, you can also post, post, sir.
இல்ல நான் போட்டுட்டே இருக்கேன்.
I also posted, sir, but yes, okay, it's okay, sir. It is posted, sir.
I am posting now that you can able to see that.
No, sir, I didn't.
சொல்லுங்க சார். Raman sir.
Yes, sir.
இந்த யூடியூப்ல தான் சார் ஃபீட்பேக் லிங்க்
Yes, sir. I posted, sir. Many times I posted. I don't know.
அது ஆனா உங்களுக்கு விசிபிள் ஆகுதா அந்த?
Yes, sir. Visible is visible, sir. No problem. Or else, okay, we will post in the WhatsApp group, sir. We will close it, okay, within 15 or 20 minutes. No problem at all.
Sir, WhatsApp la போடாதீங்க.
Okay, okay, ma'am. Fine, fine, ma'am. I'll type.
Sir, Saravanan, sir.
Yes.
Can you share that feedback link in the screen? Then only they can able to see in the YouTube.
Feedback link.
Yes, sir. Only feedback link.
Where, sir?
In the screen.
In the screen, No, if you have PPT, okay, we can open it. But the Zoom, no, actually, okay, sir. Sir, please do one thing, sir. Just copy and paste and feedback link in the PPT, sir. Just to open the PPT, sir. It will be visible in the YouTube. We ask the participants to take the photo. Natarajan, sir?
Yes, sir. Yes, sir.
Yes.
Otherwise, announce it the feedback.
Yes.
Sir, can you able to see, sir?
Just a moment. It's opening, sir. Right now, it's opening in the Zoom and the YouTube also. Started to screen sharing, but not visible. Sir, you maximize the font size so that okay, it will be visible for the YouTube stream, sir. Natarajan, sir?
Yes, sir.
Actually, dear participants, after you complete the feedback form, the certificate will be sent to your mail, your registered mail, not now.
இப்ப தெரியுதா பாருங்க சார்.
Just a moment, sir. இப்பதான் screen share பண்ணிருக்கீங்க. Now it's opening. Karthik sir and Anita Tapu ma'am. Okay, thank you so much, ma'am. You please leave, ma'am. Thank you so much for your presence, ma'am. Thank you so much.
Yeah, see you then. Thank you.
Okay, thank you, sir. Thank you so much, ma'am. So the screen is said that sharing.
Sir, wait, sir.
Okay.
Sir, now you can able to see.
No, sir. Now it start screen sharing. Sir, not visible, sir. Address, sir.
இல்ல நான் ஷேர் பண்ணிட்டேன்.
இல்ல இன்னும் வரல. இங்க யூடியூப்ல வரலையே. யூடியூப்ல அப்படியே நிக்குது.
இல்ல ஜூம்ல வந்துருச்சா சார்?
என்ன சார் புரியல? ஜூம்ல வரல சார். ஜூம்லயே வரல. ஜூம்லயே ஓபன் ஆகல. தட்ஸ் a ப்ராப்ளம். நீங்க ஜூம்ல மட்டும் ஓபன் பண்ணுங்க. It started sharing வருது. Dear participants, kindly fill the feedback form in the Zoom which you have posted now right now. Okay, the certificate will be sent to your registered mail ID which you have given in the feedback form. Not now. Sir, just now okay started screen sharing. Started only screen sharing. அப்படிதான் வருது.
ஷேர் பண்ணிட்டேன் நான். என் ஸ்கிரீன்ல தெரியுது.
But இங்க தெரியல சார். சார் நீங்க you do one thing sir, you stop share again, okay, you get the new share sir. But in the Zoom it's not visible. That's why I'm asking. In the Zoom it's not visible. Okay. Now you do the new share or again sharing. Now it started screen sharing, that's all.
தெரியுதா சார்?
No sir, just a moment sir, I'll do it. Hello. Yes. Yes ma'am. Yes ma'am. Ma'am, yes please. Sir, okay, sir, I'll open the Word and document and type the feedback link, sir. No problem at all.
Connect ஆகுது. Saravanan sir.
Sir, okay, sir. No, sir. I opened the Word file, and also, okay, I have opened one Word document and typed the feedback form. So no problem at all in the YouTube. I'll take care.
Okay. Okay, sir. YouTube la theriyudhu, sir.
Yes. It will be visible, sir. No problem.
Okay. Thank you, sir.
Okay. No problem at all, sir.
Sir, Zoom la problem illa.
No, there is no problem in the Zoom.
Okay, sir.
The registered participants, okay, I mean, who has given the feedback or filled the feedback, the certificate will be sent to the registered mail ID. No problem at all.
So those who are all filled the feedback form, you will get certificate in your mail. We are not posting the certificate in the or feedback link in the WhatsApp group or any other media. We will send you in your mail ID. Those who are filled the feedback in their mail ID, we will send you the certificate. Saravanan sir, you have to mention it daily 100, you will receive certificate.
Okay.
100 per day. சார் அந்த யூடியூப்ல வந்து கேட்டுட்டு இருக்காங்க, நீங்க அப்படியே அனௌன்ஸ் பண்ணிருங்க.
இல்ல யூடியூப்ல அனௌன்ஸ் பண்ண முடியாது, பட் நான் ஒரு மெசேஜ் போடுறேன். ஐ டோன்ட் நோ, ஓகே, இதுக்கு போட்ட மெசேஜ் எல்லாம் போஸ்ட் ஆச்சு, அந்த ஃபீட்பேக் லிங்க் போடும்போது போகல. ஐ டோன்ட் நோ வை. ஆமா, ஐ டோன்ட் நோ வை வாஸ் a ப்ராப்ளம். அது இருக்கும் போஸ்ட் குவரிஸ் எல்லாம் போட்டேன், அவரும் போட்டாரு, வந்தது. I sent the message again. So you able to see my message, sir, in the YouTube? Address, sir?
YouTube la correct sir.
It's okay. What? Okay, fine. Then why the link is not copy and and now I posted the link in the YouTube. So are you able to see? Address, sir?
Sir, YouTube.
No, no, not in that live. In the link, I mean, the chat box, I posted the, the feedback annual.
No, sir. Dear participants, fill the feedback. That's all. The link is not in the visible. We
Okay,
can't
sir.
able to see that.
So I request the participants to take the snapshot of the feedback link. So we are going to close the session. So shall we close, sir? Or else we can give the time. Address, sir?
Zoom la check பண்ணுங்க sir. Zoom la
No. Zoom. Sir, once again, you put the feedback link in the Zoom, sir. Some more participants still they are asking.
Till now, 221 participants responded.
221 participants. Oh, okay. You are also watching over there. Okay, sir. Shall we close the session, sir?
Make an announcement, sir.
Okay. What announcement, sir?
Screenshot of feedback.
I already announced. So, dear participants, okay, you please take the screenshot of the given link, and the link is already posted in the YouTube. Also, you kindly take the snapshot, sir. You please again you post the a feedback link in the Zoom, sir. After that, we can close the session. Once again, you post the link in the Zoom. After that, I will close the session.
3 times put it.
Okay, fine, sir. So, dear participants, you please take the snapshot of the feedback link, which is posted by right now. Certificate will be sent to registered mail within a week. The certificates will be issued to 100 participants per day. So please kindly cooperate. So you see the certificate within a week. Ma'am, actually, ma'am, shall we close, ma'am? Ma'am?
Yes, sir.
Okay, fine. Sir, Nadra, sir, you are the host. You can close now. I'll also close that YouTube.